All right, let's get started, folks. Um, I just want to quickly make sure that my mic is working. I see it on here right now. The last week I spoke for an entire 5 minutes before realizing my mic was muted. So if you can, okay, mic is working. Perfect. Thanks a lot for confirming. Hi everyone. We're back after a week. So for those who are not, who weren't there the last week, we are doing this x86c compiler stream where we're writing a C compiler in x86 assembly. And the purpose of this is to not make a compiler that's perfect, that's great, that's optimizing, but to understand how the process of bootstrapping works. So the idea is before the first C compiler was written, or the current C compilers that we have are also written in C and C++. So how do you compile them? And when you go back in time, the first once versions were written in assembly or object language. And they were not feature complete. Like they didn't have all the features. They basically had a bare minimum set of features that let you write a compiler that can then compile all the other features. Same goes for optimizations. These compilers are not typically very optimizing. They just get it working correctly. And that's what we are doing here. We're trying to write the whole thing in assembly, and then in the next part of this, I'll use that compiler that we wrote to then write a full version of C. Or when I say full version, again, the C language is very complicated. There's a lot of features. We'll focus on some the core features and get it working, and also implement some optimizations to show how much better we can do over the basic assembly one. And one of the goals of the assembly one is to keep it simple and to keep it small, so that we can get it done quickly and then start building on top of that. So last week, to catch folks up, we got to a point. Oh, by the way, if you're following along, if you want to take a look at the source code, I'm sort of maintaining this website on the side. It's not complete by any means, but if you just navigate to my website /x86c, it's also there at the bottom of my. Oh, I'm gonna change it to sharing screen now. Yeah. So if you look at this website here. I'm sort of maintaining all the constraints we are adding to the language. So stuff like no preprocessors, no hash defines, no if define and stuff like that, because you want to keep the language simple. The preprocessor, it's a language by itself, which is hard to implement. We are also supporting a few set of keywords, so things like char, continue, break, else, if, and so on, but we don't have everything. So for example, you might notice there's no for here. That's because we will implement, perfect timing on the screen change. I almost forgot to do that. So for loops are can be done using a while loop, so we'll just skip that for a while. You'll also notice a distinct lack of the struct keyword here. So we are not planning to support custom user defined types, at least for now. Towards the end, if we have some time, we might actually implement that. Hey, Rohan, so we are continuing our work on the C compiler. I was just explaining all the constraints we're adding on the language so that it's easy to implement it in assembly. And yeah, so we will support a bunch of operators. In fact, we'll support all unary and binary operators, function calls, square bracket operators, dereference, pointers, and stuff like that. But we won't support stuff like, custom types mostly. And the idea there is you can do a lot of stuff without those structs. Mainly when we get to the point where we write our other C compiler on top of this compiler, we should be able to do it without the structs, because structs are essentially just a way of packing things together. If we can pack them in separate variables, that also usually works. And then, of course, we are only supporting very basic primitive types too, like char, integer, long, and their pointers. Pointers to pointers, and obviously there's void here too, but it's not a type, so I didn't mention it here. So that's basically what we're going to support in types. No floating point operations. My understanding is to implement a compiler, you don't really need a floating point operation, but we'll figure it out. If we need it later, we might have to tack it in. And then there's a lot of constraints we're doing to simplify things. One of the biggest one is number 6, which is token should be separated by space tabs and new lines. So I don't want to spend too much time on tokenization, which is the process of breaking down the whole string of the program into smaller tokens that you can quickly parse. So what we're doing for now, at least, is all your tokens should be separated by a space. And that makes it easy for us to parse it. We will eventually relax this. Like at the end of this compiler, once it's working correctly, I will go back and change the tokenizer to now not require this, because the goal of this is to make it a usable language. Having to put a space after every single like token is a lot of work. But I don't want to focus too much on tokenization right now, get to something that's working, and then we'll go back and change the tokenizer to say, okay, now let's handle everything properly. We are doing parsing errors, like wherever while parsing, if we see kind of a sequence of tokens that doesn't make sense, like for example, you have a function definition, but it doesn't have like a closing parentheses. We will complain about that. We will give errors, but we'll try to keep it minimum. Like there'll be cases where we can't, like there'll be like you have to check a lot to give those errors, so we'll just skip over that, which is, it's a design decisions here. And then there's like some other constraints, like maximum identifier length is 32. So all your variables, your functions and everything will have a maximum length of 32. And that's just to make the tokenizer easy too. The way we are parsing it is all in registers instead of putting it in memory. And we're using 4 registers at most to keep track of the token. 32 is a good enough number for most applications, so we'll stick with that. It makes comparisons easy too. Like comparing 32 bytes is just 4 register comparisons, as opposed to having to go through a loop and then do like a mem compare. Yeah, and what's not mentioned here is we're not using any libc to sort of implement this. This is all in assembly from scratch. We are using GCC to compile this, but it's just to assemble it basically. There's no compiler, there's no C code involved in this. Yeah, so just to recap, that's what we were doing. And the last place where we left off was to the point we can compile and run this program, this empty.c, which has 3 different variable definitions, and then it has the main function which returns 42. You'll notice what I was talking about. Oh, why is my screen washed out? Can you guys see my screen correctly? It appears a little washed out on my side. Is it fine on the stream? Can one of you confirm that my terminal is readable? Black text is fine. The tan text is kind of close to the background color. Oh yeah, so the tan text is just my terminal prompt. Once we open the file, I think it should be fine. Let me do that. So is this all legible? Because what's happening is on my screen, when I look at the stream itself, the text is very, very like flushed out. If this is okay, then I think we should be good. Yeah, okay, that's all readable. Perfect. I think it might just be my other display settings. Okay, that's fine. So yeah, this is the program that we were able to compile. You'll notice that there's like a space after every token. That's what I was talking about earlier. We will relax this. We will, fix this later. But for now, I just want to get to like a working compiler. And yeah, so that's where we were. And for today's sort of session, I think I want to get to the point where we can actually compile. And this already runs, but we want to be able to do like expressions and conditions and so on. So we want to be able to start referencing variables. Like right now, you'll notice that the only kind of expression seems like more on your end than the stream. Okay, perfect. Right now, you'll notice that there's like constant values being referenced, but we want to be able to reference variables. Like for example, like this. We also want to be able to do operations on them like this, and then conditions and stuff like that. Ideally, the example that we would want to compile is something like Fibonacci, because it involves recursion, function calls, some operations like binary operations, conditions, and so on. So that's the thing at least we want to get to today. And yeah, we'll start by supporting variable references. So when we start like accessing variables now, local variables and global variables. But before that, I want to do some cleanup. So the last time we implemented a bunch of code, and something I was later not so happy about is how we did the tokenizer. So it's not a major change. I'm just going to make a small change, which I'll explain through. And today's stream, I'll try to explain everything I do. Last stream, I realized when I was looking back at it that I was doing things, but I wasn't explaining everything. So I'll try to do that a little more, much more this week. So if you look at that tokenizer, the main function that the parser calls is this get token function, right? And now what this get token function does is it looks at our program input and extracts the next token. into the 4 registers RBX, RCX, RDX, and RSI. So it basically keeps filling the registers one by one. Like every character it gets first goes into RBX, then if it overflows, then the RBX gets shifted to RCX, and then you sort of keep filling it, and so on. So this is fine. The only issue is once a token has been sort of like, once the application or the parser asks for a token, it's gone. Like there's no way to get the same token again. And this is fine. Like you essentially can remember the token on the application side and basically like do things with it. Like this is an issue when you ask for a token to check like if your particular thing that you're parsing for is done. Like I'll give an example. For example, you are parsing a type and you see int. I'm just gonna so suppose I see int as a token, right? Now I am not still done with parsing a type. There might be a star here, and that still is part of the type, right? Now the problem is you don't know what the next token is without you get it. Now the problem is if it is a star, great, you make it a pointer to integer and you move on. But the problem is, what if it's not an integer? Like say I see an identifier x. Now the problem is I've already passed that identifier. So even if I return out of parse type, one token has already been consumed. And this is fine. Usually like this is okay. You can communicate between your functions saying, oh, by the way, the last token that I dequeued was this, or it was a identifier, things like that. And sometimes it makes, you don't even have to explicitly communicate it. Like for example, when you are passing expressions, the end of one expression can consume the next expressions token, but that's usually okay because you can you maintain an invariant saying get expression always has one token consumed. But what happens is this makes it very hard to understand what's going on. So we want a mechanism to return tokens back to the tokenizer, like saying, okay, I read this, I actually don't like this token, this is not for me, I'm giving it back to you. So the next time get token is called, please return this one. This is basically like look ahead mechanism, right? Like I want to be able to look at a token without consuming it. And the simplest way to do that is to be able to return a token. Now, the complexity of your parser, like how much look ahead you have, depends on how many sort of tokens you can return back to the tokenizer. We will limit ourselves to one token being returned. Makes it easy to implement, and also is plenty for the language that we are supporting. Like it basically depends on how many tokens you have to read ahead to be able to resolve ambiguity. Like if you see a token and you still can't decide if it's A or B, like if it's end of a pointer or if it's if it's end of a type or something else, that's when you need to like maybe even dequeue another token. And if that helps you break your tie, you might have to return back both your tokens. That we will not support. We'll support returning just one token back. So what we're going to do now is we're just going to maintain sort of like this buffer, like a cache of token that can be filled in by the tokenizer. So I'm going to go back to the data section, and I'm going to say this one is just an identifier table. So I'm just going to put a token cache here, right? The token cache is just going to be two registers worth of space. That's because our return values of tokens are in RAX and RBX. The RAX contains the type of the token, and RBX optionally contains if the token has any parameters. Like for example, if it's an identifier, then what's the index of the identifier in the identifier table? If it is I think if it's what else are we support? If it's an integer, then we put the integer into the RBX. So we have to basically always store two values. So I'm simply gonna do like quad 0 and quad 0. So the cache is empty to begin with. And you'll notice that, let's look at our defs to make sure that 0 is not used. So we do have 0 being used as token EOF, like it's end of stream, but that's fine. Like by default, the cache can contain end of stream because end of stream is never going to be cache. Like end of stream is, end of in file is never going to be put back into the token. And even if it is put back, if we run our tokenizer again, it will again produce EOF. So that's okay. This is not an issue. So yeah, so we will use EOF as a empty cache mechanism. So by default, the cache comes out empty. Now we go to the get token function. Now here what we're going to do is the first thing we're going to check is if the token cache is empty. And the way we will do that is we can just move from token cache. a question. Maybe add ADA safety profiles to your C compiler. Eventually, we will get there when we have something working. Right now, I can barely add two numbers. Actually, we can't even add two numbers. We'll get there safe eventually. But yes, thanks for the suggestion. We will work on it eventually. Okay, so what I'm going to do now is I'm going to load a value from the token cache. Actually, we should load it in RAX, because if it does contain a value, we have it ready to be returned. Right? I'm also going to just move the second value into how do I do this? I think it's just this, right? No, I need to figure this out. Let's ask Gemini. AT&T syntax is annoying. How do I access 8 past a label? Yeah, label, yeah, just label plus 8. Okay, this is correct. So we're going to load this in RBX. And now what we will do is compare if we will check RAX, right? Like we'll check if RAX is 0. If it is not 0, we will continue to get token continue, right? And get token continue is here. And if it is not, sorry, if it is 0, we'll go to get token continue. If it is not 0, we'll just return, right? So the tokens and the extra information it has with it have been loaded into RAX RBX. We check if the token is 0. If it is 0, then we don't have something in the cache. We go to get token continue and start to like actually build a token. If it is not 0, then we just return whatever we just loaded, which is exactly what we want. And then on top of this, we also implement a function called return token, which has the same sort of I just want to make sure that I'm not adding it somewhere that overrides something. It's because we have a bunch of fall throughs here. I just want to make sure that, okay, let's do it here. So we say return token. Return token will take the tokens in the same sort of registers that we return them in, and this will just store them back into the cache. So it goes token cache IP, and then we have RBX stored into token cache of RIB plus 8. Perfect. So now we have our token cache implemented, just a way of returning tokens back to the thing. And now we can go and change our parser a little bit. So let's just go top to bottom, because we assumed in a lot of places that a token will be consumed. We'll actually simplify those assumptions. So parse_tu calls get token for the first token. It compares if it's an EOF. If it's not EOF, it goes to parse_tu. If it's EOF, it goes to parse_tu end. If it's not, it calls parse_tld. So what we can do now here is now parse_tld already assumes that that token has been read, like the first token has been read, and it tries to interpret it as a type. We can simplify this. We can say we will return this back. So this becomes, we don't want to, so the comparison happens when we jump to parse_tu end. If not, I'm going to just return the token, right? So that way we can make parse type consistent with everything. And then you call return token, and then you call parse_tld, and then you jump to parse_tu for parsing the next top level. TLD is top level declaration, by the way. Okay, and so parse type no read, we can now actually change it to just parse type, because parse type can now also read. So let's see, go here, and parse type just becomes this, and then we do call get token here. Just trying to make it a little consistent everywhere. That way we don't have to deal with having to remember where extra token has been consumed and so on. Okay, so parse type then consumes a token. the type is in RAX, which is now moved into R11. Then we consume the identifier, make sure that it is an identifier. If it's not an identifier, we complain, report the error, and then we continue, move the identifier, so the name of the function or the variable, whatever it is, into R12, and then we call get token. Now this get token will tell us whether it's a function or if it's a variable. And the way we do that is by comparing the token with, in this case, we're like looking if it's an opening parentheses. If it's a less parentheses, then we go to parse function. If it is not, then we go to a parse global variable, because if there is a opening parentheses, it must be a function. In all the other cases, it's a global variable. So this is fine. This looks correct. We have consumed the token. Now the issue is, if it's a global variable, it would either be a semicolon or equals, right? We should probably return the token here to it's fine. I mean, in this case, parse global variable can only come from this specific location, so there's no point of returning and parsing it again. Yeah, the parse global variable anyway is just right next there, so it's just easier. Okay, so then you go to parse function. These can assume that the token has already been consumed. They compare it with semicolon. If it's a semicolon, then it's a parse global end. We're done with parsing the variable. We jump to the end. If not, then we have to. We're currently reporting errors saying that we don't support initializing variables. We will simplify this later. This must mean that it's an equals to, like it must be int x equals to 5 or something like that. So this is fine. And then we go to parse global end, which seems correct to me. Yeah, this is fine. There's no changes to this. Parse global variable is correct. Let's go to parse function next. So this one has already consumed the opening parentheses, so that's great. What this does is first puts the function into the global symbol table. So you're maintaining a list of all the global variables and the functions that we have and their addresses. And the way it computes its address is by taking the current write address, which is R14. So this is the place, this is the buffer where we are generating the code, generating all the assembly code. We are storing that into the second offset of RAX. And this is fine. Then we increment the RAX by 24. I should actually change this to global table entry size, which I'm going to do now. Let's call it global table entry size. And I'm going to define this somewhere else, because if later we add more stuff to global table, like per entry, we want to be able to move it quickly instead of having to manually like go and change everywhere. So this is fine. Then we go to current function slots. We allocate some space in the stack, so we need to count how many arguments there are. So this is currently 0. Local symbol table. This is fine. Okay, and now what happens is we do get token again. And this is where we're comparing if it's an R parent or if it's like arguments. So if it's an R parent, we can go to function body, which is fine. But if it's not, we are still calling parse type no read. So instead of that, we'll just do call return token. So we will return the argument whatever it was back, and then we can simply call parse type. This makes our parse type very, very simple and like consistent everywhere. Okay, and then we check, we move the type into R11, we call get token. Oh, R11 is not being overwritten, is it? Yeah, the type has already been stored into the global symbol table, so we don't have to remember that. Okay, and then we do call get token, which will get the name of the variable. So we get token identifier. It has to be an identifier. If it's not, we report an error. So we currently not supporting function definitions which don't have identifier names. So just like no just type. And then we move the name to the R12. Then we assign a stack slot. So we go and increment the current function stack slot by 8, because all our values are 8 bytes regardless of what type they are, which is just to make things easier. And then we increment the local symbol table by storing that variable name into the local symbol table, which is basically like a local variable now. And then we look at the next token. If it is an R parent, we jump to parse function body. Otherwise it's a comma, in which case I'm calling get token here again because so we need to change some things. This return needs to go here, so that way it starts with parse type, which means we don't have to do this anymore. So you can just go back to parse in the next argument. If it's a comma, we go back to parse in the next argument. If it's a closing parentheses, we jump to parse function body, and this is where we start parsing the body. And this is fine. We start parsing by consuming the curly brace, and then first token of the next statement. Okay, so this is parse function body next, where we get the token. Okay, and what we're doing is we are checking if the if it's a closing R brace, so if it's like the function has ended, and if it has ended, we jump to parse function body end. Now, another thing we did is we assume that parse statement will always have the first token consumed. We don't have to do that anymore. So if it's not a closing parentheses, we're going to return the token, right? This is fine. And then we call parse statement. Now we'll change parse statement to not have to assume that the first token is already consumed. And then we do parse function body next. We'll just go and parse the next body and so on. And parse function body and just does whatever cleanup needs to be done for the function and then return. Now return statements can be of the form like these statements. Now we need to change it to just also say call get token. We don't have to assume that the first token is already consumed. And then call token semicolon, this is fine. J parse statement done. If it's a semicolon, then the function is the statement is done. It's an empty statement. If it's not, currently we are only supporting return statement, so we will add more cases here. If it's a return keyword, then this is fine. Jump to return statement, which is here. So yeah, so we're calling parse expression. Now parse expression we will change to also not consume the extra semicolon. So parse expression semicolon already consumed by parse expression needs to be removed. What is this doing? This is actually generating code for the return expression. So this it will do, and then we'll just call get token to consume the semicolon. Okay, and then it will go back to parse return statement was called from parse statement, right? So it will go back to here, which is fine, and then we'll go and start to parse the next statement. Okay, this is perfect. Now parse statement done is also okay. Now expressions. Now expressions, we assume that the first token. Did we assume the first token was consumed? Parse expression here. So parse return statement starts with parse expression. Okay, this is fine. So parse expression starts with its by consuming its token. This is correct. Here we are only supporting integer expressions right now. We'll add more cases here. Parse expression continue. This is okay. Eventually, we'll have to change this code to also consume the semicolon, and then check and then return it back. So not consume the semicolon. And parse integer expression generates this code, which is shoving the pushing the immediate value onto the stack, so the return statement can then just pop it and return it. And parse type also seems correct, which is getting token and then doing everything. Okay, so this has been changed correctly. I'm just gonna save everything, make and run. Oh, there's some issue. Okay, GTES, you haven't defined that. So GTES, this is global symbol table. We are currently saying 24 bytes. I'm gonna say GTES, and local symbol table is also going to be LTES, right? There's another 24 somewhere here, which is this is parse global end. This is parse global end is adding the variable to it. So yeah, GTES here. This is the local symbol table, so I'm going to make it LTES, and that seems correct. And then we're just going to define our constants up here. Dot EQU GTES 24, and then dot EQU LTES 24. Typically I would put these into defs.inc, but because this is local to this file only, so we will put it in this file. We don't want all the constants to be exported. Okay. Unexpected comma after GTES LTES 24 25. Oh, what's wrong here? Oh, this needs a comma. Okay, undefined reference to return token. Let's see. Did I not call it return token? I did call, oh, I didn't export it. Okay, so this builds. Let's quickly compile our program and see if it works. Okay, there is something wrong with it. So first error here. Okay, let's debug this. So attach a debugger. Parse tu report error loop. Okay, so what's gonna happen now is we don't have a stack trace because we're not really writing C, we're writing assembly, and we aren't following any like sort of stack frame hygiene to help GDB figure out what function we have an error from. So I have to just step through this and figure it out. I want to make sure that I want to first check if the problem is with variable declarations or with function declarations definition. So I'm going to quickly make another example where I'm just going to put a variable, right? Let's try running this. What did I call it? Oh, it's in Scratch. Okay, so this itself failed. So the variable declaration itself is failing. So, okay, we can just step through this and hopefully this will be fine. Break at parse tu. Okay, so we are in parse tu now. Let's switch to the assembly layout and then just step through this. We got the token. Let's check what the token is. It is integer 696C74. By the way, so keywords and special characters, the way we are encoding those tokens is instead of giving them unique values, just put those tokens like characters in the register itself. And because maximum length of our keywords is 8, that's fine. And the only thing that can be longer than 8 is identifiers and integer constants, which are anyway stored elsewhere. So this is fine. Okay, so 696E74, that's correct. We're gonna do next I. We get into parse. If it's a semicolon, then it should go to parse tu end. No, oh sorry, if it's an end of file, it should go to parse tu end, but it's not, so it's gonna continue. And then it's returning the token. Oh, right, because we're going to parse the type, right? So this next, you can skip over return token. We can go to parse TLD. So step into parse TLD. This will get token again. Let's make sure it is correct. So it is 696C74, so the integer token is received. Then we continue. This is parse TLD. Yeah, okay, this is fine. Wait, what is? Oh, sorry, we skipped over parse type. That's okay. Call get token will get the identifier name, which is correct, and then we should make sure that it is an identifier. Okay, so get token. Now let's make sure what the value of RAX here is. It is integer again, so something is wrong. Parse type should have consumed the token, so something is wrong with parse type. Okay, to run from the beginning. Okay. So the type has come here. Let me just go ahead. We compare if it's an integer. If it is an integer, we go to parse type end. Parse type done, returned it. Oh, we forgot. If we do return the token from the cache, we have to clear it. Sorry. Forgot about that. Okay. That was the mistake. So what we did is in get token, when we return a token from the cache, what is happening? Okay, in get token, when I find something in the cache, I'm supposed to clear it before returning. So this is just gonna be move q $0 into %x. No, not rx, sorry, into token cache of RIP. We don't have to clear RBX because that's assumed. Okay, this should fix this. Okay, this ran either correctly or no, it didn't run correctly. Failed and passed to you. Okay, break. Now to step through again. Oh. This caused some issue. Get token returned wrong. Move 0 into token cache of RIP. That seems correct to me. Should is this crashing? TU is translation unit. We'll just step through it and see what happens. Is this failing? No. Oh, did I not add a return statement to the... Oh. Return token. I did not add a return statement. Well, that would do it. Okay. Okay, this is fine. Now it's complaining main function not found, which was expected because the function doesn't have a main function. Okay, now we go back to parsing our other example. Invalid statement. Okay. Invalid statement. When does this come out? We'll check. Break parse du. So the first time it's going to be 3 variables and then functions. I'm going to continue. This is second variable, third variable, and function. And now we, oh, why did I continue the third time? It's fine. Control C, run. Continue, continue, continue. Okay, and then we're going to step through. Compare RAX, it's not going to be, so next I, parse to next I, return token, I can just do step SI, right? Yeah, okay. Parse TLD, parse type. Oh, I think it's invalid statement comes when you don't get the return token. Okay, so we will fix this. Okay. So parse type should be fine because we are passing the function right now. Let's go to the function body actually. Parse function body. Break parse function body. Continue. Okay. Now this calls next I. Oh, it's this itself is failing. Interesting. Yeah, this is some GDP issue. I'm going to sometimes it like even if you like next through a function directly goes ahead. I'm not sure why that is happening. Okay, but we are here. Let's go next I. Oh, why does call get token itself? Okay, I'm gonna try this again and step through this. Okay, so it is getting the next token. So just finish. Finish goes to oh, get token. Did I again forget return value? No. There is a get token end somewhere, right? Get token end. Yeah. Then it sees a space or yeah, it goes to get token and eventually should return. Okay, I have to step through this now. Okay. Okay. What we have 7b, which is it is opening curly brace. Perfect. This is what it should be. I think it goes through one of the the last one maybe. Okay, so it goes to special token character. We have already consumed the directory. Just go to read till end, which just keeps on consuming tokens till we reach the end. Okay, which should happen immediately because there's a space / new line somewhere. Compare 21. Okay, and we have found the space, so now just go and consume the spaces. Okay, dcr10, this is fine. Move rbx rax, this is fine. We have the token in rax, which we should check here. Is 7b, perfect. I think this return is what is getting screwed up. No, it did come out. Yeah, this is a weird thing with GDB. For some reason, if I just go through the function, it crashes. Yeah, okay. This is annoying. So this is the second consuming token. So let's just check if we got the right token. We didn't get RB. Okay. Here, step through another one. Let's try next time. Okay, it is fine. p/x. So now we got the name of the function, which is, sorry, no, this is the return keyword. R72, yeah, RETURN. Okay, this is correct. So we are comparing 7. Okay, we are checking if it's a closing parentheses, which it should not be. So this goes to parse function body and no. Return token. So token, that is the return keyword, is being returned back. Okay, this is fine. And then parse function body next. No, it goes to parse statement. So I'm going to step inside. Call token. That should give us back the return keyword. It is the return keyword. Okay, this is good. If it's not a semicolon, it's not. Then we check if it's the thing. So this should be fine. Parse return statement. That's good. Now we do parse expression, which should be okay. Okay, and then we generate the code for this. We finally okay, why is there a get token at the end? Oh, this is the semicolon, right? Yeah, we parse the expression, pop the semicolon, and then return back. So I'm going to quickly check if this is correct. Oh. So parse return statement is what is causing the issue. No, I think it's just this GDB. If someone knows a fix for this, I would really appreciate it. step I, nothing in the cache. So special character, consume spaces, ready to return. I'm gonna check what it is. It should be semicolon, right? 7D. No, it's curly braces. Huh. I guess the expression consumed the, yeah, I think parse expression consumed the semicolon and didn't return it. That's what happened. Okay. Parse expression. Right. This is just wrong. So we consume the integer. We call get token. This should not be called. Yeah, we don't want to consume the last expression. Okay, this ran correctly. Great. Make sure that the return value is correct. Here it is 42. Great. So why not use GEF? Saves a lot of keystroke. What is GEF? I don't know what GEF is. Do you wanna tell me about it? It might be helpful. Is it like a GDB command? GEF. Oh, GEF is GDB plugin. Okay, let me look that up. I don't have Vimium installed in this, do I? Okay. GEF GDB plugin. Oh, it's GDB enhanced features. Interesting. I will have to spend some time understanding this, but does it support entirely agnostic? This is good. I mean, I do have some of my own macros written that I include sometimes for specific things, but yeah, I mean, I guess it's just a good collection of things. Let's just look at script. Yeah. This is just the release script. Where's the actual? Oh, it generates it. Never mind. Okay, I'll check this out later. Might break your GDB init. Yeah. I guess I'll check this out offline, and maybe in the next session we'll use it. But thanks for the suggestion. I'll keep it in mind. Yeah. Okay. We are back to the point where we were last week, with the exception that we have the return token implemented. Now I want to start implementing expressions where you are referencing variables. This should be easy. This shouldn't be very hard. So we have parse expressions, right? So this first checks if it's a token integer. If it's a token, it goes to parse integer expression. We'll just compare it to token identifier. If it's an identifier, then we go to jump parse identifier expert. We'll have to check both global and local symbol tables to make sure that it's one of them. So that's why I'm going to a separate section. So we go to parse identifier expert. Okay, so we should first check in the local symbol table, and then we should check in the global symbol table. So we need to iterate to the local. We should make a helper function to find a local symbol table entry or a global symbol table entry. Putting the code everywhere is just annoying. Yeah, okay. So we're going to make a helper function now. Which could go with this, right? Okay. So we're going to do get or check global table. So yeah, this is going to just iterate to the global table and find that specific entry for us. I think I already have a routine for this. This is storing stuff into the global symbol table. This is also storing stuff, so we don't really have a checkpoint. Okay, Uh, so our identifier would be in RBX, so we can use RX. Should move the start of the RIP into RAX. We immediately check if it's the end of it. So compare RAX with global symbol. There should be a global symbol table end, right? Yeah. Global symbol table end of RIP. If it is equal to the end, then we do global table not found. I should use local labels for all this, which like start like this, but it's okay. This one should just return. If not, then we do comparison. Compare. The first entry is what that matters, right? So it's identifier, index, code gen, address, and type of variable. So we can just compare the first one with RBX. If jump on not equal, we go to check global table next. Right? But before we do that, we have to increment. Okay, then check global LEAQ. We use LEAQ because it doesn't affect flags, so we can still do the comparison. And if it does match, we just want to return the global table entry in RAX itself, which is annoying because we just incremented. Fine, we'll just decrement it again. Yeah, this is annoying. Anyway, so now we have a check global table function. I'm going to simply also implement a check local table function. I think this should just be and this just become LTES. Yeah, I think this should be fine. Okay, so now we have a function that goes and retrieves entries from global table for us. We were doing parse identifier expression. Okay. Okay, so we will immediately just call check first local table. Right? We need to know if we found it. So should set it to something else. Not found should just return null pointer if we didn't find it. Okay, good. Okay. Compare. Check if it is 0. Jump on not 0. Parse identifier exper local. call check global table test q %rax jump on not empty, should be jump on not zero. Identifier x per local. Identifier x per global. If not, we just print an error. So we do move q error invalid variable. Invalid. This is good. Okay, so we can report an error, and now we do per local. Okay, parse local, no, parse identifier x per local. So this is actually pretty straightforward. The variable is already on the stack slot, and the local symbol table tells us what the stack slot index is. We just have to load the value from it, push it onto the stack, and then return. That's basically what the code we have to generate for this is. Okay, so in RAX we already have the local table entry, right? So our local table entry is identifier, index, stack slot, offset, and type of variable. So we might actually have to look at type of variable for this to know how many bytes to load. Actually, no. Let me think. We will store our values in 8 bytes stack slots anyway. The only issue is sign extension. If it's we'll store it in sign extended form already, so we don't have to do the math when loading it. Yeah, we'll always store it in sign extended 8-byte values, so this should be okay. Okay, let's go to check local. This is okay. What was it? Parse type. Okay, yeah, so all we have to do is take the stack slot index, which should be in 8 of RAX. So move q 8 of RAX into RAX should be okay. We have the stack slot, and now we have to see what code to generate. So okay, so this is what we were testing here, right? We want to move 8 bytes from a particular stack slot. So let's say 1, 2, 3 of %RSP into RAX, right? And what's the instruction encoding for this? So okay, so the instruction sequence is 48 8B 7B. Sorry, I think the 7B is the offset, yes. And then we have 48 8B 05. Good. Okay, so we need to generate these 3 bytes and then 4 bytes of the stack slot offset. Okay. Should we use, actually we should probably use RBP to do this. Yeah. Yeah, we can't use RSP because we are using a stack machine. So this should be, oh, also I wrote RIP for some reason. My bad. Okay. This one. Yeah, it should be 488B45. This is for a single byte offset though. We probably want longer because, I mean, it still supports 64 local variables. Yeah, it's okay. Let's just support more. So 0xFF88, for example. Let's just generate the general encoding, which is longer instruction, but it's fine. Yeah, so this is going to be 488B85 followed by 4 bytes of the stack offset from RBP. Okay. That was our look. Okay. So we have the stack offset. Okay. Is the stack offset what we're storing multiplied by 8 though? Good question. Let's see. Current stack slots. This is for checking. There is a, yeah, this one. We are incrementing by how much? No, this is just resetting it. This is where we're storing it. We are incrementing current stack slot by 8. Okay, so we already have the multiplied by 8 value. Okay. So the RX version is already here. Okay, so we now do move B. How many do we have to generate? 488B85 and 3 bytes. Okay. Yeah, just do it easy. 48 into, I think it was R14, right? Yeah, code gen area is R14. So then we move this into R14. 48, what is it? 488B85. We can optimize this, but it's fine. 85, right? 4B85. And then we do move L EX into 3 of R14, and then we move this by 7 bytes. Okay, and then this is all, yeah. Oh, we need to push the value too, sorry. Never tested that. Can we merge this actually? Do we need to do move and push? Is this a valid instruction? If I do, I think they should be fine. Let's check. I am not sure if this is valid, but you can check. Oh, it is valid. You can push values from memory. Okay, then let's just use this encoding. It's only FFB5 then. This is easier. Okay, so local identifier is fine. Okay, this is good. And now let's do parse identifier expr global. So global is easy. We already have the address in the global symbol table. We just push the value from that address. The unfortunate issue is the address is a 64-bit value, so we'll have to first move it into a register and then dereference from it. Yeah, I don't want to use RIP relative addressing for this. We'll just move the 64-bit constant into RAX and then pop from it. I think specifically for RAX though, we can do memory operations. This is fine. We can just do move ABSQ. So let's do move ABSQ dollar. I need a big value, so FF12, FF34, FF12. This is 1, 2, 3, 4, 5, 6, 7, and then 8. Okay. Into RAX, and then you do push Q. Yeah, I need the encoding for this one. Okay, so it's 48B8 followed by, why is it 0, 0 here? What did I miss? Oh, it's a name. No, this is fine. Why did the constant not appear? Interesting. Why is it showing 0, 0? I mean, it'll just be the constant there, but why is it not showing this? Why is it showing 0, 0? Why is it like a linker thing? Huh. Is linker supposed to handle this? Seems wrong. Let's try it. Yeah, undefined, right, undefined reference to, but that's, oh, because I didn't do, yeah, that's why I was complaining. Okay, that's correct. Okay, so it's 48B8 followed by the 8-byte address. So we need to first get the address from the global symbol table entry, which is the second index again. Perfect. Okay, so we do the same thing as before. We move the value into RAX, and then what was it? 48B8. What I'm doing right now is I'm actually generating the instructions, and I'm using like writing it in assembly, just getting what the bytes are, and then putting those literally into the code generation area. I keep remembering 48B8. And then we have to store the whole 8 bytes, which I think we can just do with move Q. Yeah. All right. Yep. And then what's the next instruction? It's FF30. FF30. Okay. So this should be 10. Yeah, 8 bytes. I can merge these into like a single instruction, but it's just easier for me to read this way too. I'm not going to bother. And then AQ. All right. So we did 48B8. then the constant for 8 bytes ff30. Oh, it's ff30. Okay, so this is the global table load, and the rest should just handle this correctly. Okay, let's test this out. Where were we at? Parse expression. So parse expression, yeah, here. So we wrote token identifier, token expression, and let's just return out of it and go back to the statement. Perfect. Let's try this out. Of course, we had error in function parse expression, parse identifier expression, parse identifier. I always make some mistake in identifier spelling. Yep. Identifier, and then identifier local. I think that should do it. Okay. Let's make sure everything is working first. Okay, good. And now we're going to change the example to reference a variable. So let's say foo. It's 0. So foo is probably uninitialized. We will now make the change where we can parse global variables with values. This is all simplifying now. Adding more features. Let's go to parser. We had the global var, right? Yeah, this is parse global variable. If it's a semicolon, we did parse global end. If it's not, then it must be a equals to something. We have already consumed the equals. We should just make sure it's equal though. Token equals x, jump on not equal val. Gotta dip in a few minutes. This was cool. Yeah, thanks for joining. Hopefully by the end of the stream we will have working Fibonacci. I'll post everything on YouTube, by the way. If you I don't know how you know me, but if you just go to I'll put the link for the YouTube channels somewhere too. So there should be, if you just search my name, this is, oh well, I can just copy it from here. Yeah, so this is my YouTube. I'm gonna put it on the website, project repo, Twitch link, YouTube link. Also, okay, you can, yep, the links have been added here, so you can watch it later. All right, going back. Okay, so jumper not equal parse global error. Parse global error. You're gonna say parse var no init. Just gonna change this to parse var bad. Gonna say fun to spring a little surprise. I won't tell you name, but here, but I'll be taking a COVID test later that I'll tell you everything you need to know about. Sorry, what? I won't tell you my name here, but I'll be taking a COVID test later that will tell you everything you need to know. Interesting. I'll think about that later, but thanks for the crumbs of clue. Fun to spring a little surprise on you. Haha. You bet, you bet. All right. I should go back and remember which one of my friends are not well right now. Okay, but take care, please. If you do have COVID, please isolate yourself for a little bit at least, and make sure you're taking all the medicine and hydrating enough. Okay, variable declaration expected assignment or something. Okay, let's go to PE. I don't have COVID. Penny will drop. Talk to you soon. Perfect. Oh, you will have to. Okay. Okay, and if it is not equals to equals, then we have a. Did I call it equals or did I call it assign? Oh, it is assign. Equals is double equals, so this should be assigned. Okay, and what this is going to do now is just generate code for parse expression. Actually, no, we can't do parse expression. It has to be an integer, or it can be like an expression, but it should be constant evaluatable. The annoying part is parsing, like evaluating expressions inside the compiler is gonna take a while. So the easiest thing we'll do is we only allow integer expressions to appear in the initialization or address of other variables. So we'll do that later. Yeah, okay, so it should be basically an integer. The problem is if I just call parse integer, it's going to push the value onto the stack in the generated code. We don't want that to happen. We're just generating code right now. So, I mean, one way to handle this is to generate sort of like what is called like a global constructor function that gets called before main runs, which will go and evaluate all this code. But anyway, C doesn't allow runtime expressions to be evaluated in global initialization. C++ allows that by calling constructors. We will just allow integers only. So what we should do is, the token assign has been consumed. We're just going to say call get token, and it should be an integer is what we'll say. And we'll compare it with token integer. And if it's not, we'll just say, I'm just going to go here, parse global error. It's fine. Use the same error. Okay, and now that it is an integer, we know what the value of that integer is in RBX. So just going to store this value into the variable. Okay, so parse global end creates a global symbol table entry and increments RAX R14 by 8. So what we're simply going to do is also pass the value. Okay, now the value is in RBX, so we can do jump to parse global end, and parse global end will assume that RBX contains the value. Right, so we will just write the value here. Actually, if it is uninitialized, we should initialize it to 0, right? So if it is semicolon, we will also, I think RBX should be 0, but I don't know if it is, so we will clear it. Okay, so we'll clear rbx, and then we'll jump to parse global end. Imagine reading ISSC and implementing line by line. Exactly. That's someone has done that. I mean, people have done that, and I have immense respect for that. I don't have the energy for it, so I'm going to implement a subset of the language, which I will decide on the fly. And then once we have a working compiler, maybe in C we will go through the whole ISOC standard, which I have pinned somewhere, and then implement it. I don't promise anything, but we will try. Okay. So rbx has the value. We just have to make sure the value is stored into that location. So this is simply rbx into r14. And store the value into r14 and then increment r14. Okay, so this will have the value initialized. Okay, this works. Let's go and try to change this to now have a value equals 13, for example. Okay, parser expected type. Oh, there should have been something is still wrong. Okay, let's debug this. Parse global variable. No. Oh, break. Wait, why did it jump to parse global end? Oh, the ZOR cleared it. My bad. This was in the wrong place. Okay, so this is fine. We can do this earlier. Okay. Oh wait, I didn't make it. Sorry. Okay. Is 3D, which I think should be equals. Perfect. So it's not 3B, it is 3D. So this should go to get token, which should parse it. It should be an integer, which I think it will be. It is integer. If it's not equal, we oh, the semicolon was never consumed. That's what happened. Yeah. Okay. So before we go, we need to, yeah, the semicolon was never consumed. So if it's equals, assign, let's see. So how do we consume that? Yeah, just before going, we do call get token, but before we call get token, the value needs to be stored, whatever the thing was. I mean, I could already put it into R14, but just write the value out. That would solve it. Nah, we should just store the value somewhere else. I don't like this, but it's fine. So we will have the rbx saved. Then we go to parse global end. This will make sure that the semicolon is consumed in this special case. Okay, with code 15, which doesn't seem right, but x86 example empty.c echo $13. Yay. Okay, so we got our variable reference correctly, and this is good. So now we have global variables we can refer to, and we also have hopefully local variables to refer to, but we haven't really set up the RVP in a way that global variables can be local variables can be referred. So I'll do that afterwards. Let's just do some expressions. I want to do expressions. Okay. Parse expressions. Okay, so we have done integer, we have done identifier. We do have to support unary operators and expressions too, but let's just do binary operators first, because that will help us do some reasonable expressions. Okay, so binary operator. The way this is done is at the end of any expression. Okay, when you start parsing expression, you also look for, hey, is there any more expression coming up as part of the same expression? And if it is, like, the only possibility can be either a function call. Actually, I forgot that. Optionally have also a function call with arguments. This is also one of the expressions we can have. Okay, so we'll just look if the next token itself is binary. When we're doing expression, we're going to look if the next expression is a binary operator, and if it is, we'll generate code for the binary operator. So let's do that. I'll first write a simple example of addition. We'll test that, but then eventually what I want to do is I want to like make a generalized code generation for expressions. Instead of like writing each case by hand, we will just make like a binary operator table, which will have all the operator types and the corresponding code to generate, and we'll just pick up values from that, which will make it very easy. We'll have to just like do some math on it to make sure that we like maximum instruction sizes are the same. I mean, the maximum is what we are putting in the table. Okay, so let's do parse expression and add the case for optional binary operator at the end. So where does it go? Yeah, so parse expression continue is currently just returning. So what this does is jump to parse identifier expression, parse integer. Oh, jump to report error. Okay, so these should not return directly. These should go back to parse exper continue, because we have to check if there is more expressions to parse. Parse exper continue. Right, so this goes back to this message, which is currently returning. But instead of returning now, I'm going to say where was the semicolon being consumed? Oh, it's part of the statement, so that's fine. Okay, so now what we'll do is we'll call get token again. We'll check if it's semicolon. If it's semicolon, oh no, sorry, we will check if it's one of the binary operators. If it's a binary operator, we will pass the binary operator. If not, we will return. Okay, so let's start by writing a simple plus operation. So we will compare token plus, right? Yeah, it is plus. Token plus x. This has to be a function call though, because expressions can be recursive. We just can't jump to parse. We want it to be recursive. It'd be nice to have it recursive. Actually, let me think. Let me think if I should call here or jump. I think call would be better. Okay. So compare token plus jump on equal parse plus expr. Yeah, right now I'm handwriting these cases, but eventually make it into like a general binary operator parsing. Okay, so jump on equal parse plus expression. Which will come back to parse expr continue, and then it will return. Okay, this is fine. If it's not, then it must be a semicolon or whatever. We don't know what it is, so we will do return token. Right? Yeah. If it's not a binary operator, it could be the semicolon, it could be whatever. So we will just return it back and then continue. So statement will handle returning the semicolon. Okay. Now let's do parse plus expression. Okay, so what parse plus expression needs to do is the plus has already been consumed and we know it's a plus. We need to first parse the next expression. What are we adding to? So this will now call parse expression, right? This will ensure that the next expression is parsed. This also decides the associativity of our operators, because whatever is afterwards will all be consumed. This is where like having parentheses helps. Like if we want some specific ordering of operators, we would require the users to use parentheses we're not implementing precedence in our parser. That's a little bit of a deviation from the implementation. I should fix that later. Okay, so call parse expression. So it gets the two expressions on the stack. So both the sub expressions are now on the stack, one after the other. What now plus needs to do is pop the two values, do the operation, and push the result back. So one way to do this is generate code for popping into RBX and RAX, and then putting it into RBX, or I guess RAX should be destination, and it doesn't really matter. So we simply have to generate the code for pop q RBX, pop q RAX, add q RBX into RAX into RBX. For add it doesn't matter, but it matters for other operations that we'll write. It will follow simple. If I remember doing infix postfix in compiler long time ago. Yeah, for the parser it doesn't really make it that complicated, because what we're doing is to implement the recursive structure of the parser itself, we're using like function calls in the assembly to sort of handle that for us. Precedence is a little tricky, like where to end, right? Like if you see when you're matching to the right hand side, where to stop, and that's how you implement precedence. But I'm not really doing that right now. I'm just going to say if you need some specific ordering, put parentheses around them. And then this does push q RBX, right? Yeah, okay. I just want to generate code for this. The pop q and the two pop queues and the push queue would be generated in a general way for a binary operator. The add or subtract or multiply, whatever, will be generated by like a generalized binary operator implementation table. But for now, I'm just going to do this. Okay, so it is 5B 5.8 for the pops, and then add and 5.3. So let's just generate this. Move B 5B. Ideally, I should define constants above for specific instructions and then move those instructions, but this is fine. 5B 5.8. And then we have the add instruction, which is 4801C3. I'm so tempted to just write it as a single instruction. Yeah, I think this one I should write it as a single instruction. Yeah, because you'll have to put this into a table eventually. It'll be easier if we just do it as a single. So actually, I'm gonna do the push along with the instruction itself. So 4801C353. But the way this value will be encoded is, let the NTNS will have to be handled. Okay, so I think this should be 0x53C30148. Yeah, 53C30148. 53C30148. Right? Yeah, into, this needs to be move L 2 of %R14. Yeah, so what we'll do is we'll eventually make this constant a general one for any expression, and that will help us handle it. Okay, and then the 6 bytes. Yeah, 6. Okay, and then we can go back to jump parse x per continue. I mean, ideally I should not jump to parse x per continue. Ideally I should just return, because I should say that, okay, you have seen one binary operator, you're not allowed to eat any more binary operators. But that is annoying, so we will just continue to parse x per continue, which will go here. We'll call token again, check if it's plus. If it's plus, it's fine. If it's not, yeah, sure. I mean, do the rest of the binary operators and then call return token and red queue. Okay, this is fine. Why did I write jump queue everywhere? All right. Let's first make sure it runs correctly. Already failing. What did I do wrong? I guess we will check this. Parse x per continuous causing segmentation fault for some reason on. 3b, which is semicolon. Oh, put the $sign. Okay. Okay. Something happened, which was 15. I think this is correct. 30. Okay. So now we will just try a simple expression here. Let's say plus 5, 4. 13 plus 4, we should get 17. Yeah, we get 17. Perfect. So we have a simple plus expression working. I want to quickly add other binary operators too. So what we're going to do for binary operators is, instead of having a like an expression table for like a case for everything, we're just going to make a binary operator like table. So this goes into, let's put it here. Sure, it's in data. We have binary operator table, right? And the format for this is going to be 16, no, not 16. It's going to be some number of bytes. The first will be the token itself, which is the like operator. So 8 bytes for operator, followed by 4 bytes for instruction, including push. So this is the what we maintain in the binary operator table. So quad token plus comma, and this is where what we put in the plus goes. So how do I store 4 bytes? Is it just long? Okay. I'm gonna ask Gemini, make sure. JSON 4 byte equivalent of the dot quad. Not long. Okay. Yeah, so this is going to be our encoding. And at the end, I'm just going to put $0. $0. Okay. So it's going to be a 2-step process. So here in the integer parse itself, instead of looking for token plus, we're going to just iterate through the whole table and check if it is a binary expression. So we got the token already. Now we are going to start matching it. So move q. We can't use rbx because the value, it might not be a operator, in which case rbx needs to be preserved. So we'll do rcx. Binary operator table into rcx, right? Okay. First we check if it's empty. So we say test rcx comma rcx, jump on 0. Let's parse expr end. Yeah, if we have reached the end of all binary operators and it's none of them, then we go to parse binary expression end. Actually, we should go to parse binary operator end, because there might be function calls, so we'll have to add that later. We'll just okay. If it is 0, then it's fine. If it's not, then we compare it with the token that we have. So, oh wait, this is the value at RCX. Annoying. Okay. If it's 0, then go to RCX. If it's not, then we compare it to RBX. So this still becomes this. Okay. We do increment the value. I hate this. Let's increment it at the top. This is binary table entry size. binary operator table entry size of RCX, and then have to do a negative one here. Okay, check next binary operator. Okay, if it matches, jump on equal, you go to parse binary operator expression. Yep, this is correct. Compare RCX with RAX, this is correct. Otherwise, jump to check next binary operator. Okay, so this will put it back to check the next operator, and it will increment RCX and then do the comparison. Okay, we need to now change the +1 to just do parse binary operator expression. Is it just parse binary operator expression, or what did I call it? Binary operator expression. Okay. And now this one is easy. We do call parse expression to get the second expression. We do pop x, we do push x. The only thing we need to do is make sure that our RCX is preserved, because RCX is what contains our table entry for the binary operator. And then this one goes here. We need to move the 4 bytes from there into R14s, like into the slot. So we can do move Q 8 of R14 into R14 into RCX into RCX, and this should be move L. So this will load the value, and then this will move the value. Yeah, okay. So just loading the value from the table and putting it into the instruction location. RCX has been saved before that, so this is correct. And then it goes back to parse expression continue. Okay. And if it's not found, then it just goes to return whatever that token was and continue. Okay, seems fine. RCX use itself 271. Borders, yeah, okay. So borders is 6 for us, right? Yeah. If we decide to make our instructions longer, this will be easy to change. Cannot be used in making a PI object. Relocation against this. I think this is the instruction for that operator. I think it's just failing. Yeah. What does it say? This is not supposed to have dollar. Oh yeah, it's just supposed to have. No, it's supposed to have a dollar. Using somewhere else? No. Does this work? Nope, this doesn't work either. How do I put constants in here? Zero x2b. Oh. this works. Why is this not working? Is it because of long? Quad. For some reason it doesn't like long. No. Oh. Something is so wrong here. I have done quad 0 before, right? Like tokenizer was, there was a, oh, when storing constants, it's just without the dollar sign. Okay. My bad. I'm surprised though, how was it working earlier when I have the keyword table? Oh, it was just the keyword. Okay, my bad. Okay, this works. Let's just make sure that the addition works correctly first. Obviously something fails. Let's debug this. I'm guessing it's gonna be somewhere after this. No, it's before that. Interesting. Oh, I know what's happening. No, I don't know what's happening. Okay, it's failing even before parse expression. We haven't changed anything. Okay, let's try without the function. Okay, this itself is failing. I don't know why. What did I change? Okay, parse TLD fails. Parse type fails. Okay. Oh, it got identifier where type was expected. This is just literally the first one. Where did the type go? Okay, I think I know what's happening. This is parts TU. Goes to parse TLD. It's already at identifier. Where did the type go? Do I have a spurious call token somewhere? No, parse T is the first one. No, this is... okay. I think I made a mistake with the identifier. Did I move something in the tokenizer? this is fine. Remove something here. I mean, it's supposed to know that it's a keyword int, not an identifier. Why is it saying it's an identifier? I think I changed something. Yeah. This only has these changes. That doesn't change anything. Yeah, this is going to be hard to read. I'll just have to step through it. The first token itself, for some reason, is showing up as integer. I'm going to make sure why that is happening. Okay. This checks if the cache is empty, so we can do next I, next I, next I, next I. Okay. We load one value. Is I, okay. We should go to identifier and keyword. It's good. Go to read to N. INT, great. Then it goes to space, consume spaces, okay, and then get token N. There's code somewhere to check if it's an identifier or what. Okay, yeah, this is fine. Didn't I add code to make sure that it's an identifier? Consume token goes to. Okay, let's see what this goes to. Oh, read till end was a call. Okay, sorry. Steps through, then store and. Oh, RCX is not cleared. My bad. Okay, yeah, that's what it cost. Isn't it our responsibility to clear RCX though when in get token? That was the issue. Oh no, get tokens tokenizer. Get token clears RCX. For some reason, RCX has some junk in it, which is causing it to think that it's an identifier and not a. Could have figured it out at first sight with GF. Yeah, I will look at GF after this, get myself acquainted with it, and then I will use it the next session. I mean, I've just been using GDB all my life. I haven't really used plugins for it, except for my own plugins that, I mean, I have a paper on extending GDB without, for DSLs without writing plugins to encode like DSL specific information into a generated code. It's called Detox. That's the only extension I've used. Okay, let me step through this and Okay, store identifier. No, again, what is RCX here? 0. It is 0. Okay, so this shouldn't be a problem then. Is this even correct? Jump on not equal. Test doesn't set equal, it should be just not 0. Okay, it was a flag issue. Here it should. Oh, I did write JNZ. Okay, I'm officially lost on this. That is 0. Okay, so it does go here. Now it should go and check. Okay, and what is the REX at this point? 69. Okay, that is INT. Okay. Oh, it immediately jumped to store identifier. So identifier table, keyword table. Why is it 0? You move address of keyword table into RAX, you subtract 8 from it. Wait, did I change here something? This is wrong. How was this working before? Did I change something? Yeah, this should be here. Check next keyword should have LEAQ8 RAX of RAX because, yeah, how am I comparing 0 directly? I guess there was just some garbage earlier that was making it work. Okay, I guess this should run now. Oh, still bad. Okay, so check next keyword. I'm going to put a breakpoint on this one actually. Compare 0 with RX. Yeah, this is for some reason failing. Okay. Zero /x RAX is x86c. Okay, that is correct. Load the value into the table. This seems to be correct. I'm just going to dereference this and check what it is. So cat star $RAX is H. Why is it H? Should it be char? Keyword table. is H? Capital H. X16 star keyword table, right? No, it should be ands. 16c star ampersand keyword. So that's byte, number of bytes shouldn't be C. Keyword table has unknown type. Cast it to its declared type. That's what I'm doing. Fine. I think it's just wrong. The keyword table is starting with keyword char, which is 63686172. What is 72? Just checking. It's R. It should be R. I'm trying to debug this again. Okay, I'm gonna check this again. It is 63686172. So this is CHAR. Okay, great. Next, I. Oh, there's another LEA here. Okay, skipping over some tokens. Okay, my bad. Okay, this should fix it, I think. Okay, thank God. Okay, now example. What was happening was when I added this LEA here, there's already one more here which I forgot to remove. And the reason why this needs to be here is I start, like, I have this -8 here, so it needs to be incremented. I think what I had done previously maybe was I had added a dummy entry uh, to this table, or it just happened to start from like a non-zero value before this, which is, I think, yeah, the reason why this is happening. Yeah, it's just like, I think what's happening is parser.s came after tokenizer, and then this is maybe like 0 caused it to be non-zero, and yeah, it's like, yeah, we were making mistakes. But I think this should work fine now. Let's try. Okay, echo $? Okay, it works. Okay, now let's try more operators. Let's do subtraction. God, this took forever. dot quad token minus. It's called token minus, right? It is called minus. Okay, and what I simply need to do now is find the instruction for it, which you can do here. Sub q percent rex rbx. For debugging reasons, I'm going to keep all of them. I think it's imlq, right? Yeah. I think I used iml somewhere. Yeah, it's imlq. Okay, integer multiplication, and then idivq for division. I will do these 4 for now. So let's compile these. Idiv does it not I? Yeah, it's not idiv. Divide to signed integers, 8-byte integers. idfq, but idfq probably has fixed registers. RCX, okay, you divide by your divisor. Now you specify divisor in the instructions. What is the dividend is an RAX, so good. So this just becomes RBX then, right? And what does the result go into? I just look at idfq. So reading Gemini is bullshit. Sign div. I see. Div R64 is what we want. Div sign divide RDX RAX by, oh, it takes RDX and RAX, so RDX needs to be zeroed out. No, it needs to be sign extended. So it means if RAX is negative, then RDX needs to be set to all ones. Okay, we'll do that later. RDX RAX by R6 by RM64, okay, with results stored in RAX quotient and RDX remainder. Okay, so what we need to do is change some things. So since the result by default goes into RAX, it will be easier if we do push q RAX. Yeah, so yeah, we'll do this instead. idfq rbx, this is great. Okay, these 2 instructions. So this happens to be a 4-byte total, not a oh, mul is longer. Yeah, see, this is what caused the issue earlier. Yeah, I might have to make the instructions longer. I think I'll have to make them 5 bytes. Okay. Which, but 5 bytes is gonna be annoying. I have to do 2 loads. It is what it is. Can't do much about it. Okay, so yeah, is there a way to do it in 4 bytes somehow? In x86 is there an instruction to multiply 264-bit values where the encoding is 3 bytes? Single operand version of both mul for unsigned Oh, okay. Let's go. We should just use this then. iml of reg. It does have one of this form, iml r64. The output is in, it takes rdx rax and puts the output in rax. No, sorry, rdx rax is the output of rax and the values. Okay, so we can just do rbx. Okay, yeah, this is easier. So rbx is the second value, rax is the first value. We do just rbx. We do rax here. Okay. This way it's 4 bytes only. Okay. And this is fine. Okay, so let's do subtraction first. It's exactly the same, except instead of it's there actually. So 29 in the middle. F8 F7. I'm just gonna copy this. Star. Star. EB F748. Div. FB F748. Great. Sorry, this took a while, but I think we should be good now, and we can handle different. It's not token div. What did I call it? Divide. Okay, let's try doing some subtractions now. $247. That's wrong. 13 minus 4 should be just 7. No, just 9. Sorry. What is happening to me? Okay. We'll check this. We'll check multiplication first. $52. Okay, everything. 13 times 4 is 52, right? Okay, this is correct. I think what happened is I did the subtraction in the wrong order. Yeah, that's what happened. Okay, this is correct. It's 13. Okay, so this one, I think I just did this order of operations wrong. Yeah, I think it just became 4 minus 13, not 13 minus 4. So subq rax rbx. What we are popping is the second value into rbx, the first value into rax, and then pushing to, okay, I'm just gonna check subqs. What is the destination register when two values are used? This one. Subq is subtract R16. Subtract the second one from the first one. That is correct. And the result goes into the second one, right? Destination equals to of course it's destination equals destination minus source. So it should be 48, 29, D8 and then 50. Okay. Is it? Sorry. Okay, this is correct now. You're getting 9. That's good. We'll have to fix the RDX to be properly computed too. I think for division at least. For multiplication, it's okay. The overflow is going away. That's fine. The higher bits for division need to be set for negative values correctly. Like it needs to be sign extended into RDX. We'll handle that later. Okay, good. So we have basic multiplication, addition done. What other binary operators do we want to support? So we have ampersand is unary, exclamation is unary, comma, plus, minus, divide, percent. Percent is, I think, exactly like div. Instead of using RAX, we use RDX. Okay, this is easy. Should we just support this? Okay, this is fine. What else? We have assign. So assign is a special case. Assign is assign is special in that it's not really it is a binary operator, but it needs the L value of the left hand side. So this is something we have to handle separately, where the first expression that we parse, we actually would change it to always be an L value. And if it's a binary expression, we'll first convert the L value into an R value and then do the operation on it. And for assign, we'll keep it as an L value. So assign we'll handle later. Let's do equals, less than, greater than, and all these ones. So for equals, we have the two in RAX and RBX. So to make sure that they are equal. So we ideally want to return 0 or 1. We don't want to, so let's just ask Gemini. Given two values in RAX and RBX, how can I implement the equals operator to get the result 0 or 1 in a register? You can use setCL. Set the low byte of RCX to 1 if they were equal, otherwise 0. So we first compare. Oh, crucial, set E only modifies the lowest 8 bits. That's fine. We can clear the destination register. That's fine. And then set CL. Okay. Shouldn't the XOR be before that? I guess XOR doesn't set the equality bit. I don't know. Okay, so we do clear one of the registers, we do comparison, and then set CL. Okay, this should be easy. Let's see. So we do CMPQ, RAX, RBX, and then set set on equal %CL. Okay. We'll make sure that the RCX is free, is emptied out. Sorry, 0. Good. This is very long instruction encoding. Well, let's ask it if set E can be done. Can set E be encoded in a single byte? If not, we'll have to make our table longer and then put some no ops. Fine. Multi-byte instruction due to how the opcode map is structured. Fine. So we also need to do a push after this, right? Because it's gonna be in RCX. Yeah. Yeah, these ones are a little annoying. So we could do 2 separate tables for operations and comparisons, or we could just make everything consistent. What's this length? Where did the push go? Okay, so this ends up being 7 bytes as opposed to 4 bytes from earlier. I think the best is if we just make it 8 bytes and then make it a quad, so we don't have to work with. Yeah, that's probably the easiest. Let's just make it a quad and put a bunch of no ops. No op is 0x90 in this, I'm guessing. Okay. Make it 8 bytes. So 9. This is what, already 4 bytes. 1, 2, 3, 4. Okay. 90, 90, 90, 90. Okay, and this becomes quad 0. Now this one. Token equals dot quad 0x90 51 C1940FC3. Okay, so this is gonna give us the equality comparison. We have to change BOTS to be 8 bytes plus 8 bytes, so 16 bytes, and this should now not just load a single byte, it should load a quad into RCX, get RCX done, and increase by 8. No, not 8. 8 plus 2, 10. The first 2 pops were 1 byte each. Okay, this is good. It's 12:30. It's only 2.5 hours in, and we have gotten at least some binary operators working, so I'm happy about that. Let's do token not equal. What is it? So we have equals, not equals. Not equals will be easy to do, so let's just do that first. Dot code token not equals. We do have to generate the instruction to clear RCX though, so that needs to be remembered. Just 94 becomes 95, I think. Yeah. Right, just 94 becomes 95, everything else is the same. Okay. What else do we have? We have less than, greater than. Let's do those two. There is a thing for this, right? Yeah, so we have less than is set L, set G, set LE. Is there no set GE? That's annoying, but okay. We'll do the ones that we have first. So set token less than. Less equals. What did I do? What did I do? Okay, let's get there. So less than is set. I'm just going to copy this a bunch of times. So this becomes set L, set G, set LE. I'm going to just try my luck and see if set G exists. It does. Okay, so it's 9C. Okay, so set L is the same quad with, instead of 9.5 it's 9C is set L, right? Yeah, set G is the same quad with 9F instead of 9C. Less equals is 9E. And this is 9B. Okay, so we have all our binary comparison operators done too. We should make sure that it works though. Unit tests would have really helped. This is subtraction. Now let's do equals 0. That's correct. I think this needs to be this 1. Okay, correct. Less than false, less than equals true, greater than is false, greater than equals is true greater than, oh, true greater than equals to 3 is coming out to be wrong. Is this gonna be correct? This is also wrong. I think I might have screwed up the order again. Yep, the order is screwed. How do I get this so wrong? Subtracting the second operand from the first operand. Okay, so these need to be changed. $48, $39, $8. 48, 39, D8. Let me change these manually. I don't have the energy to think about this too much. Okay, there's all operators done. This is correct. This is correct. This is also correct. Okay, perfect. So now we have our comparison operators working correctly. This is great. We can reference variables. We can do comparisons. We should maybe do conditionals next, right? We should also do assignments next. Actually, I want to do assignments next. Okay, we'll do assignments. So to change assignments, we'll have to support assignments. We'll have to actually change a lot of get statement, parse statement. So currently what parse statement does is it looks for keyword return and then it calls parse expression, right? I mean parse return statement just calls expression here. So parse expression now, by default, when it gets the expression, it should not give you the value of that expression, but the address of that expression, which is a little tricky for non-L values. But we need to somehow support this. So what I was thinking is we could just use two stack slots. Like we could just push the value and the address if it exists. So for non L values, it'll just be a null pointer, so which means you can't assign to it. But if it is an R value, so if it is an L value, then we'll put the value and the address. And so we don't have to know what we are assigning to. Again, the reason for this is till we have parsed the expression, we don't know what we are going to do with it. So that L value to R value conversion, actually, so the right way to do this is always generate the L value for the first one first, and then generate code to do the conversion from L value to R value by dereferencing it. But the problem is when you're parsing expressions, you never know what you're going to see, right? Yeah, I'm thinking for parse expressions, we will just put both the value and an address on the stack. Makes this easy. If the value address exists, just do that. Okay, so parse expressions need to all change. So parse expression has multiple cases. So we have get token. If it's an integer, then we do parse integer expression. So parse integer expression pushes this, right? So we just want to push another 0. Also, I kept saying that I have to clear RCX and I never did that. Gotta go, happy streaming. Thanks for attending. You can watch the rest of the stream on YouTube afterwards. Sorry, RX. This one, 4831C9. So I need to store this one. Come on. So it's 10 plus 3 now. Yep. Okay. It's 13 byte per binary operator. We also have to change it to push addresses of stuff. So I mean, could do the smart thing, but we want a working C compiler. We don't want a lot of stuff. So I just need to know what the instruction for pushing 0 is. 6800. So 6800. Probably an easier way to do this, but 6800 should be fine. So we have integer expression, right? So we also need to add this 6800. I'm going to make a macro out of this because this is going to be required a lot. And did this. Yep, so this pushes the value, then the address. And the good thing about pushing the value and then the address is that we can pop it off without having to use an extra register. Push value, push address. Okay. Identifier expression. So yeah, identifier expression is going to be slightly different because this will also, so this will first put the value, but then also put the register itself. So in this case, what was the encoding we were using for local expression? This is the global one. I need the local one. It was related to RBPV, right? Oh, we have to do the LEA separately now. Okay. So the LEA is 488D85. What was it for move? What have I written? So not to RC, RAX. Oh, it was, get some weird math. Oh, what is the instant that I wrote? For local expressions, I wrote FFB5 and then the address. What is FFB5? Oh, it just push the value. Yeah, it was pushed from the RBP. So we're going to change this now. We're going to do LEA and then this. Okay, so this way we will have yeah, this is the instruction encoding we are going to do, and this is also going to have the same thing. Right, so we will load the address, push the value, and then push the address. Great, so let's do this. Load the value, push the address. And then save it. Four eight D 85, then the offset 488D85, then the offset, then Okay, so now we have 488D85, then the 4-byte value, then we have FF30, which pushes RAX, and then we have 50. Great. And then parsecs global also changes slightly. This is 48B8, then the address, we have FF30. Let me just do one more. Why is there only 13? Yeah, it's 3 bytes more. Yeah, perfect. Okay. FF3050. Yeah, okay, this is good. So binary identifier and expression global is done. A binary operator. This should just do push null PTR. But we also need to pop the null PTRs. So we need to discard them. Which can be done with here. So we'll change this. Just repeat these. RBX, RBX, RAX, RAX, right? Yeah, okay. It's just these RBX, RBX, RAX, RAX, okay. And then this just becomes 4, 5, 6, 7, 8 bytes from the 7. 7 plus 8, right? Yeah, Q, so 8. So then 15, and then 4 bytes from, no, 2 bytes from this, so it should become 17. We added 2 bytes here and we added 2 bytes here. Okay, perfect. This will be 17 bytes encoding for a binary operator. It's expensive, but it is what it is. We could optimize this a little bit, like we could just collapse all the bytes into a single one and maybe also put a length field into the binary operator expression table. But for now, we'll do this. Okay, so it just pops RCX, calls parse expression, then clears RCX, pops RBX, pops the address, pops the values, does move, and so okay, this is great. And now we can do parse assign. So the binary operator, that's just a separate assignment check. So we compare the same value here. So compare token assign comma RAX jump on equals parse assign expression. So assign expression should also first compute the RHS. This is going to be RCX, call Q parse expression, or Q. Okay, so we have the right hand side now. This will all be the same, which means we can just copy this over. Yeah, so we have the first two values popped. We just need to store the right hand side. Oh, but here's the difference now. We don't want to discard the address of the left hand side, so this actually needs to go somewhere else. Let's see. So it's going to be something like popq rbx, this is right hand side address, then popq rbx right hand side value, then we have popq rax right hand side left hand side address, and then we'll do popq just use rcx, it's fine. Last bytes we want. Let's do a single 4-byte load. Five nine 5 8 5p 5p into %r14. Okay, and then we want to move values and push things out. So now we do move q %rbx into %rax, right? And then we push q the same value, so we do push q rbx and then we do push null pointer. Okay, actually I should just try. Wait, is assignment an L value or an R value expression? Can you assign to an assignment again? In C is the result of an assignment expression an R value or an L value? It's an R value. This is an input. Okay, you cannot do this. Okay, so you can push 0. This is 1 2 3 4 5 6 it's 6 bytes anyway, it's fine. We'll just do a 4-byte encoding and then do push null ptr. Move L $0x 5318 8948. And finally we do push null ptr and then increment by 10 bytes. Yeah, assignment is relatively easy. You don't have to do any arithmetic. It's just pop values, and I should probably write these instructions down as comments on top of it. I'll do that later. An expected end of file and macro. Is it macro end? End M. Okay. Yikes. Here's segmentation fault. I don't know if it's in the execution. Okay. It is running. It's failing when running. Okay. Oh, the return. The return didn't pop two values. Ah, that's what the mistake was. Here, parse return next parse statement, parse return statement. Okay, this should just pop both the values and return the second one. Doesn't put a breakpoint in that. Okay. So this takes the address of foo, pushes it, then pushes the address, then pushes 3. Why are we integers are being moved like that? It's fine. Then we push 0. Then we clear out RCX, and we pop RBX, that gives us the second value. Then we do pop RBX, that's fine. Why is there a push 0 here? Should be a comparison, right? Yep, this is wrong. Comparison instructions are wrong. But either way, it's still pushing RCX and OP. Okay, this is also wrong. Okay, this makes sense. This is wrong. Okay, let's fix the thing one by one. Oh, no, this was a mistake. This should fix the done statement at least. pointers are just wildly wrong. What are we doing, by the way? Doing f2 greater than 3. Okay, here. So this clears them out. This reads the value. Then this moves the 8-byte value from the table into RCX and stores from there into R17. This seems correct. Pushes null pointer. I just did the math wrong here. So this seems right. Shouldn't this be 16? No, push null pointer is 2 bytes. The value is also 8 bytes. That's 10 bytes. So for comparison, it should be one of these instructions, greater than equal to, right? So it should be these instructions. And then push null pointer, which is 2 bytes. Right, to debug this. Where's this add AL coming from? Yeah, this is causing the issue. So it's 9x comma 16. Okay, so 9051 is correct. 90 is from the NOP. 51 is from the push RCX. And then we have, actually I'm going to change this to 16C. Not 16C. B. Kidding me. Of course it's the other way. 16xb. Okay, 51, 90. Yeah, these 0 are coming from somewhere. Okay, these 0 there's 2 zeros in the middle, then there's 58, 58, which should to push null point. Oh, I think the push null pointers are just not getting inserted. I know what happened. I know what happened. Oh god. I didn't write the macro correctly. Push null PTR. This was wrong. Yeah, what is this 8 and 9? This is wrong. This needs to be GSM macros parameters. I think it's just %1, %2, right? Oh, you can make them named. Assign was also wrong. This is going to be 8 plus 15, and this is going to be 8. Yeah, that was what is causing it to get erased. Okay, this seems correct. 1 is correct. Okay, I'm gonna quickly check. Okay, okay. Now assignments. So we're gonna do int foo2, and then we're gonna do foo2 equals foo plus 12, and then return foo2. So now you have global variables being referenced step by step. Oh yeah, at the end of the statement, whatever value exists needs to be popped off. Yeah. We have stray values in the... But this is right now a parsing error. But the other change we need to do is, if there's a statement that doesn't have any, like, okay, the end of the statement, you should just also generate code to pop off the values. Yes, and but for some reason the parsing is also, oh, this is semicolon needs to be spaced out. Still invalid statement. We will check why that is happening. Okay. Parse function body. This is the annoying part. I don't know why it just doesn't work. If I do finish, it doesn't, it just goes all the way to invalid statement. I should put a breakpoint on the address after the two get tokens. Come on. Okay. Part statement. So we are at the start of the new statement, which is the assignment. So we do next I comparison. Okay. We check if it's semicolon, which it shouldn't be. Then we move oh, we never allowed standalone statements. Yeah, the only statement we supported was expression, so that's a problem. Okay, that's pretty straightforward. We just need to support standalone expression. So if it's not, if it is an identifier, then it's not of an expression. Is that generally true? No, it could also just be an integer. It could be a operator and whatnot. So if it's not one of the special things, then we should just go to parse expression, right? So instead of doing this, we do jump to parse expression statement. Yeah. First parse statement done. When is this? Okay, that's when this is semicolon. So what does this do? Oh, but the token that we have consumed needs to go back into it, so parse expression can work. So call return token. Right. This one will call parse expression and then just pop off the two values, which is use any of the two. Any of the pops we can use. This 58. Move this 58 into 14 into percent or 14. And we also have to do get token. Okay, this is good. Parse empty statement is what we will call it. Okay, this is good. Move X. Oh. Move S, right? Sure. Yeah. Okay, we got something. 25. Is that correct? That is correct. So we have assignments working properly now. Let's go. If assignments working, we should now support local variables so we can start doing recursion and stuff. Function calls. Yeah, I'm gonna take a quick bathroom break. I'll be back in like 5 minutes. Let's take a break till 1:30 p.m. Oops, sorry. It's okay. I'm just gonna change this here. Stream will continue at 1:30 p.m. EST. Alright, I'll be back, folks. Right, let's continue. Uh, so we have our never mind. We have our addition and assignment working correctly. We need to now do. I just want to make sure that other types also work correctly. So let's say bar, for example. I mean, everything is signed external to long. So see, this is, oh, because we didn't do this. This is working correctly. Char won't work. Needs to be truncated. We will have to take care of truncation separately. Basically, whenever loading values, we'll have to look at the symbol table. So not the symbol table. Yeah, the local or the global symbol table, and then truncate values accordingly before returning. Yeah. Okay. Do that later. Now I want to do arguments. So arguments are a lot of work, honestly, to the function because there's a couple of things that need to happen here, right? You have to reserve a stack slot so that you can refer to that identifier just like you were referring to it before. We have to have a calling convention that's easy for both the caller and the callee to implement. And the easiest thing to do is to basically follow the same calling convention that we have been following for our operators, which is push the respective arguments on the stack, then call the function. The annoying part of this is that the arguments would be below the return address, so we can't really pop them. I mean, we shouldn't be popping them anyway. We just need to construct the right offset from RBP that will like give us the address of those values. So what we're going to do now is at the function setup, we're going to push RBP and then move RSP to RBP. That way we will have our stack frame beginning, and then we'll have to do some math to figure out how far is that argument from the RBP. Now, one thing that could work is if we do negative. So like positive stack slots can be, positive stack slots would be for local variables, and negative stack slots would be for what should I call it, for arguments. Still the annoying part is like when we start parsing arguments, we don't know how many arguments there are, so computing the negative stack slots is a little annoying. We could, however, do it in a cool way by first, when you're starting to parse arguments, we pass them in a positive order, and then after we are done parsing all the arguments, we go back and make them negative. So when we pass argument number 1, it gets stack slot 0. Then we do argument number 2, it gets stack slot 8 and 16 and so on. And then once we're done with all the arguments, we go back and flip the sign of all those. So they become like -8, -16 and so on. And that, I think, should solve our problem. Yeah. And then we zero the stack slot allocation again. But we also need to, yeah, that's what we'll do. And the clearing of the arguments would be done by the caller. So if it pushes n number of arguments, it will pop off n number of arguments. So we won't have to adjust for the negative stack slots. We'll only have to clear up the positive stack slots, which is all we need to know anyway. Okay, so this should work. Okay. Let's go and change it. have parse argument. Yeah, so okay, so what this does is it initially we set current function slots to be 0. This is fine. I think this needs not to be 0, it needs to be somewhere like initialized to where the arguments would begin, like on the negative side. I will do that later. Yeah, we'll have to do the math in such a way that like and these won't be two sort of like slots. It'll just be one slot because they're pure values. When you pass something to a function, you don't pass like the L value of it, you pass the R value. If it happens to be an address, then you're passing by doing ampersand, which does the L value to like, yeah, I mean it converts the address into an R value. So yeah, it'll always be an R value. Let's just draw something, maybe let's make this easy for ourselves. What can I draw? Let me draw.io. Yeah, so we'll draw a stack here. Oh God. Let's make a function that takes two arguments, right? So let's say we're writing foo int comma int. Okay? This is what you're writing, suppose. So the caller would set it up like this. Let's say int a comma int b. Right? So the caller would set it up by first putting a value of a, then inserting value of b, then it would there be the return address. Come on, how do I copy? We'll have return address, then we will have old RBP, okay, and then RSP would be pointing here. I forgot how annoying our draw.io can be. RSP points to the last address it wrote at, right? Yeah. Okay, so, and then we will have locals after this, right? So let's say we have local 0. And yeah, local, let's say 1. So we will have to compute their offset. So the first values offset will be RBP plus 16. Stack goes towards smaller values. Yeah. So yeah, it'll be RSP. This will be RSP and RBP both, sorry. This is actually, no, sorry, this will be RBP. And this will be old RBP. Okay, yeah, so we have RBP plus 16 for the first argument. and then RBP plus 24. So we start with actually, yeah, let's just do this. We start with 16, just do add 8. At the end of it, just zero it again, and then do minus 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 for local variables. Yeah, let's just do that. This is just easier. Yeah, parsing argument is separate anyway, so let's just start from 16. So current function slots become started initialized to 16. Every time we pass an argument, we do increment it by 8, which is correct. So we do current function slots, load it into RBX, we increment it by 8, and then we store it back. Great. And this RAX also becomes, no, RBX becomes the address we store at. So yes, this is correct. Okay, so now after this we go to parse function body. So first thing parse function body would do is, before consuming the token, it needs to do some cleanup too, which is to set the current stack slots again to 0, right? Because the local symbol table does have the variable argument name stored, so we can ignore them. We just, yeah, okay, so these are the positive slots, so we do 0 here again. Okay, and then we have to make sure that when local variables are passed, they are added. Okay, we'll take care of local variables later. For now, we just want to do arguments. Okay, but we need to set up the stack frame, which needs to happen after parsing the body. Yeah, so the way we set up a frame is push q %RBP, move q RSP to RBP, and then when you are leaving, it's like what, leave ret, right? Leave does the opposite of what this does. I'm going to quickly check this. Leave instruction x64. High level procedure exit releases the stack sum pointer by an earlier enter instruction. The leave instruction copies the frame pointer into the stack pointer. This is correct, which releases the stack allocated space. The old frame pointer for the following procedure saved by enter instruction is then popped from the stack into EBP, restoring the calling procedure stack frame, and then a return instruction is commonly executed following the leave instruction. There is an enter instruction, is it? I don't know this. Oh, there is an enter instruction. Make stack frame for procedure parameters. Creates a stack frame comprising of the space for dynamic storage and 1 to 32 frames pointer storage for procedures. Oh, it can also take parameters. Is there one with no parameters? I guess I'll always do 0. It's fine. We'll just do a normal push RBQ. Okay, so leave is C9, C3, which needs to go into our return statements anywhere. Okay, so we have push RBP, move RSP, RBP. This is these instructions. So move, I guess we can just do a 8-byte instruction. Sorry, 4-byte instruction. So we have prepared the stack frame, which occupies one stack slot, and the return address is the second stack slot. So okay, this is correct. Now we should be able to start referring to addresses. The only thing we need to do now is also add the leave to ret. So parse return statement. This is what generates the C3. We need to generate C9 before that. Perfect. Yeah, so now we have stack frame setup and leave. We should check this once. Correct. Okay. So stack frame is being set up and released correctly. So one thing we didn't do is, what if the statement doesn't have a return statement? When the body is done, we should also do leave ret. So maybe that's what I'm going to do now. I mean, if it's a wide function, we still need to clean up correctly. We just can't. And so here, final parse function body end. We can just do the same thing here. Move p $0xc3. Honestly, I should just jump to this address instead of, yeah, because we might have to do more stuff later on in terms of function body cleanup. So I'm gonna do that here. Move p C3. Okay. No, this is wrong. I think what we had earlier was fine. I mean, we can do this better by doing this, calling get token, and then doing call parse function body end. So like do whatever needs to be done for function body cleanup. Let's just give it a good name too. Function body cleanup. Gen function body cleanup. Okay, this is what we'll do. Gen function body cleanup. Okay, this literally does, yeah. So if you have to generate any instructions towards the return, we should be able to do it here. And I think this needs to call this. Instead of just following through to it. And then do its own return. Because we might have some stuff to do, not in the generated code, but like in the compiler for handling the close of the function, like doing some patching or whatever. I'm not sure yet, but we might have to. So that code needs to happen only once, not every single time. So you're gonna have a gen function body cleanup separately, and then you're going to have function body end separately. Okay, this is good. Great. test this, make sure it runs correctly. Works. Okay. Now let's do function. Let's make sure that first parsing for function arguments even works. I'm gonna call it something else. So we have int bar of int x. This will return x plus 1. And then we have int main return bar. For now, let's just return 0. Okay, works correctly. Perfect. So now we need to do the call operator. So we have bar, and let's call it with 1. We can just do return here. Okay. So what this should do is call bar, get the return value from it, and do it. And the return values we are doing in arrax, and the reason for that is eventually the main also has to return, and it's fine to do a stub where if you do like cleanups, we can just return it in arrax, and that's fine. Okay, so how do we do this? Return bar 1. So we have to parse at the end of parse expression, we have to check if it's a function call operator. Yeah, so parse expression continue, check binary operator. Now check assign, and if nothing is there, then we also do function calls. So cmpq $token l parent rax jump e parse function call expression. Now function call expression, yeah, this is fine. So we have already passed the L parentheses. We need to now pass expressions till we see close parentheses and keep pushing their values on the stack. But as soon as you push the values on the stack, do remove the address. Okay, so we do get token to check if we are ending with the function call. It could be an empty function call, like with no parameters, so we need to handle that first. So call get token, compare token r parent x, jump on equal parse function call expression end. Yeah. We will also have to keep track of how many arguments have been used. We'll have to like put it somewhere in maybe a register. But when calling recursively, we'll have to make sure that that register is not messed up. Yeah, we could just like keep pushing and popping. That's what we'll have to do. Okay. because and the reason we need that is at the end of the function call we have to go and pop that many off. um, so yeah, do some math for it. So what we'll do is actually just keep, instead of it keeping it in the register, we're just going to put it on the stack. So okay, if it's closing parentheses, we just directly jump to call function parent end. If it's not, we have to return it. So we do return token, right? If it's not a closing parentheses, we return the token, and then we say parse expression, right? But before we do that, we have to just push $0. This is the number of arguments that we have so far collected. I could do stack frame setup here, but and then use RBP to keep track of local variables, which might actually be better instead of pushing and popping. Yeah, let's just do that. So this is going to do push Q RBP, move Q RBP to RSP. So the function call expression is for the first time now going to use stack slots. So we'll use -8 RBP for number of arguments, which we are going to set to 0. Good. Then we call get token. Then we call parse expression. Once we get the expression, we know at the top of the expression there is the address which we need to remove. So we're going to generate a pop rbx, which was somewhere here. Yeah, pop rax maybe. Of the pops, yeah, here 58. So we will generate a 58 here. And then we need to increment the number of arguments. So we do add q or increment -8% RBP. Right. So what this does is we're keeping track of number of arguments. And now we do again get token to know if we have more arguments or not. And if we get comparison to $token r parent, then we go to jump equals parse function call expression in, right? Otherwise it must be a right. If it's otherwise it must be a comma. So we don't return that token. We just go back to parse next argument. Parse next call argument. And so this keeps on incrementing the argument count And remember that the function that we are calling itself is also on the stack. Um, because the first thing that happened was we evaluated the expression. Uh, yeah, we first evaluated the expression, then we evaluated all the arguments. So that must also be in the stack. Eventually, we'll have to like get it from the stack, the value, and then call the function. But that's okay, we can do that. Okay, so currently the stack, like the program stack layout for the generated code is basically function target address, which is like a symbol. Then we have address of that, which is null pointer. Uh, Actually, no. Functions will have it the other way because it's a global symbol. The first value would be like some garbage, which is like 8 bytes at that location. Then we will have the address of the function itself that we are calling, so it will be like slightly reversed. Okay, that's fine. And then we will have all the arguments and their addresses, but we have to make sure that those addresses are popped off, which we have done. So yeah, okay, that's good. So we have a function target, a garbage, function target, address, argument, values. Great. And so this goes to parse call next argument, and this is fine. And then we finally go to parse function x per n, which would have consumed the r parentheses. Great. Now we have to do the actual call. So parse function call expression. Never actually called this, we just jumped here, right? It's going to create a problem. Parse function call expression sub. Yeah. Okay, this is fine. Okay, parse function call expression n. What does this need to do? First, we need to compute the address, which is going to happen by moving. So instead of incrementing, we could just that way we directly have the yeah. Now somehow we need to get the function call address. So we have in RBP the slot. Okay, if the number of arguments was 0, this would just be 0, which means wherever RSP is pointing is where the address is. So we do RSP plus this. So we move RSP comma first we Oh, I need to generate this, not so. Okay, first we move that value into a register. Right? Okay, so we have the address offset for the address into RAX. Now we need to generate RS, like an actual move that moves that into a register. So can't do a pop. Okay. Function call dispatch. Do move q 0x88 of RSP into RAX. Right? Yeah. Okay, so we have this value. And then 4-byte offset. 48 8B 8424. We do 4-byte moves. Move L 0x24 84 8B 48 into R14. So this moves the address of the address. No, this moves the address directly into RAX. We also need to call, so let's do that. So this moves the address of the function to be called into RAX. Now we simply need to do call star RAX, right? FFD0. D0FF. This moves the function call. This makes the actual function call. Now at this point it's returned. Now we need to first remove the arguments. So, oh wait, I forgot the offset to be added. So %ex comma 4% R14. Yeah, stack slot in streams 8. Okay. So 4 bytes of that instruction, 4 bytes of offset, 2 bytes of the call instruction. Now we need to actually clear off those arguments that we had gotten. So how do you do that? 1 2 3 4. We just add to the RSP that value. So that's done by LEAQ 0xFF 5. So of RSP into RSP. Is this allowed? Okay, it is allowed. So it simply does this, right? Wrong place. info, move L, x24, A4, 8D4, 8. And that was 2, so this becomes 10 of %R14. So this removes all the arguments from the stack that we had passed. Finally, we also need to remove the address of the function and the garbage value. So we need to pop off 2 values from the stack and then push our values. Now I could just increment. Oh wait, I still have to do the offset though. So I can do move L %rex, 14 of R14. Before this, I could just do incremented by 2. This popped off all the arguments too. Popped off all the arguments and the 2 addresses. And finally, we just have to do push RAX and then push null pointer, because RAX contains the address. Yes. So push Q %RAX. Move L $0x50, $15 R14. No, sorry, 18. And finally, we can be done. So EQ19 of %R14 into %R14. Okay. This is great. Now we have the function call expression completely done. So this is the actual function call, this one. This needs to be cleaned up before we go. And that does it. Yeah, I forgot to do LEAQ here. Okay, this looks correct. Let's test this out. Yeah, it's a function call expression. The return value will be on the stack. If it's if it ends immediately without any use, then it will be popped off the stack. If it's a return, then it will use the return value. This seems correct to me. Yeah, this is correct. This is my call. 85. That's wrong. It was supposed to be 2, but we got 85. But it did not crash. So that's a win for now. Let's debug this, why it's doing it wrong. Okay, here it is, main function. So we push RBP, move RSP to RBP. Perfect. Then we move the address of bar function into RAX. We push the address, push the value out of the garbage there is into it, and then we push RAX itself. Then we pop RAX. That's wrong. Just pop the 2 values and then leave red. And what happened to the function call expression? So we check for binary operators, check next binary operator, check for assignment. If it was not an assignment, then we check for L param. What is L? Wait a second, there's a thing called L param. Oh, why didn't this complain? Oh, I never compiled either, otherwise it would have compiled. $354. Okay, there's some parsing issue, but we can handle this. Shouldn't be a problem. And there's some issue on here. Okay. So we jump into this, do next step I. That itself fails. Okay. I moved RBP into RSP, but RSP into R. I'm genius. Did I generate at least correct for the stub? Yes, the stub was correct. Two, so it's an integer, which is correct. Oops. How the hell is return token saying invalid expression? No idea. It is an integer. Goes to parse integer expression, which is correct. Generate code to push the value, parse expression, continue. Doesn't see any binary operators. Doesn't see any function call. This is invalid expression. Okay, so it's failing inside parsing the argument. Where am I using invalid expression? Oh, if it's not identifier, if it's not integer, but it's actually comma, right? No, this is wrong. Should put a here. And check what the token was. Parse expert error. Huh? Okay. $7D. What is $7D? Corny Blaze Scrolls. Yeah, a bunch of tokens got skipped over trying to read parse expression. What could be the reason for this? I'm calling this side. So it's somehow here. And this is parsing in main. This is failing in main. This works fine. It happens with main. Okay, so when it starts parsing this, something is going wrong. Oh. Okay, thank God. Okay, we are in the main function now. Let's see what happens. Okay. So we move a triple or a bunch of 58180, which is the address of, should be bar somewhere here, right? Yeah, here, A180, right? Yeah, A180. Okay, so then we push the value of whatever the bytes there are. Then we push the value of the address itself. Then we move 1 into RAX and push that. Then we push null pointer. Then we pop the null pointer out. So we have 1 at the top of the function stack now, right? Yeah, okay, yeah, we have top of the function stack. Then we move this into RAX. Let's check what that is. Oh, that itself, yeah, that's a big number. Why is the stack offset that high? I think I know what happened here. We corrupted one of the registers. -8% RPP here. No, we didn't write it correctly. So initialize move to 0. Keep adding it by 8 every time. And then we finally move that into RAX. We should put a break here. Yeah, this is wrong. Why is plus minus 8 of RPP. Let's do this. So this should be 0 now. I had to call 8. Oh, my bad. That was dumb. Okay, so what is $RPP minus 8? That's the value. And what's the value there? I'll dereference it as a long star. It is a large number. Okay, so what is... Oh, we haven't done that instruction yet. Come on. It is 0. Let's go. Okay, so SI. Finish. Next I. Why is this big? Should also put a breakpoint on this, maybe. Yeah, why is this so large? Where did this come from? Something is corrupting RBP minus 8. Before calling this, let's see what it is. It's already large. Is RBP being modified by something else? Okay, no, maybe the tokenizer I messed up. No, I'm not using RBP for anything. step through this very carefully. To define a macro for this. Define. Okay. So it's DD98 is RBP and the value is 0. Okay, something corrupted the stack slot. And there was get token. Get token somehow overrode. Oh yeah, because I did not create the stack frame properly. Oh god. I did not move the RSP. I didn't move RSP to RBQ. Need to create a stack slot, right? To reserve that space too. There we go. Now it runs correctly. $228. That's wrong too, but okay, so this is the new one. Okay, thank God we have the right value this time. Okay, let's check what is happening. It is the correct value. Step into RX. GDB is really struggling with this. Okay, so now this one is taking value from RBP, like 16 bytes below, which should be correct. It should be 1, right? Oh wait, I screwed up the order. Yeah, this is wrong. Let's go back to draw.io. So offset computation is somehow wrong. Let's check. So this is fine. Plus 8 is the return address, correct? Plus 16 is 1. Yeah, so then because I did LEAQ, not move Q. Why did I do LEAQ? God knows. No, this should be right. Because we take the address first. Yeah. Oh, wait. Yeah, this should be fine. Yeah. Let's just. Okay. After this, there should be 1 on top of the stack. So RAX, RBX should both be 1 at this point, right? Both are 1. Perfect. Gets added. This gets pushed. It's 2, yes. Okay. Why is it A? Should be 8 plus 16 equals 24. Why is it only 10? Because I added 2 instead of adding 16. That makes sense. Okay. This mostly seems correct to me. Come on. Should just do finish on our next I here. Okay, this is good. P dash x dollar RAX is 2. Psi. Where did this garbage come from? I pushed RAX. Oh, I didn't push 0. Yes, I didn't push 0. I need to push null pointer. Function call expression end. What's this? Push null PTR. And then this becomes 21. That's segmentation for. Oh, push null pointer didn't specify what. 19? Yeah. Yes, yes, this worked. That worked. Let's go. Now we have function calls working. Just gonna quickly make sure that this is correctly working too. So we're gonna do minus bar of 0. So this should return 1. That is correct. Okay, so we have function calls working, although I think argument orders are screwed up. Multiple arguments is not gonna work, I think, because we didn't. So what did we do? Global variable function argument, parse argument. Yeah, so this one I think we made a mistake. We incremented it by 8. So the first argument would get like, yeah, this needs to be fixed. So after parsing all the arguments, we need to go and fix the table. How are we going to do that? How are we going to do that? Basically, what's happening is when we compute the addresses, value A comes first, we give it stack slot 8 or 16. This one gets 24, whereas it should be 24, 16. So we need to like somehow flip those orders. I mean, one thing we could do is we could give it decreasing values. Like we could give it, to begin with, we could give this 0, this could be -8 and -16 and so on, and then go and add the negation of the last value. Yeah, that would be correct. So if I do like 0, 1 or like 0, 8, whatever, and then at the end the value will be 8, so then we go and subtract that from all of them. Yeah. Okay, so assigning stack slot becomes minus here. Current stack slot gets initialized to 0, and at the end of parsing argument, parse function body, we need to go and fix the table. So call q fix local symbol table. Fix local symbol table for args. Fix local function table for args. So currently they would have values 0, 8. We need to make them, this needs to become be 0, 8, and the top would be 8. No, the top would be 16. So we just have to go and subtract 16 from both one of them. No, not 16. 16. No, first of all, have to add the negation of, yeah. So at this point, it would be minus 16. Yeah, so 0, minus 8, minus 16. We first negate that, so it becomes 16. And then we go and add that to everyone. So 0 becomes 16, minus 8, and then we add further 8 to it. Okay. So first thing we do is negate the value. Move q current function slots of RIP into RAX. We IML q minus 1. That must be an easy way to negate. How do I negate a 64-bit integer in GSM? Destination equals, okay. So simply do negq RAX and then add q, add q $8 RAX. So this will give us the right stacks, the offset value, and now for each stack slot I need to go to the local symbol table and update them. Where is that check local symbol table code? I could just use that. Yeah. So we first move the local symbol table into the beginning. Fix local symbol compare to the end of local symbol table. If it's equal, fix local symbol. Comparison is not required. Just to add q. %RBX into 1 of %RAX. Yeah, because not 1, sorry, 8. The first one is the identifier, the second one is the of actual slack slot. Then we do increment. This is not required. This is not required. This just becomes jump fix local table next, and then we have fix local table end, which just returns. Right, so we now have fix local function table for args, move the current function slots into RBX, negate RBX, then add 8 to RBX. That makes it like one more than the, yeah, okay. And then take the start of the local symbol table. If it's the end, and stop. This looks correct. Add to the entry. Move to the next. Okay. So current stack slots have been made 0. This is fine. Okay. Fix local symbol table for args. Fix local function table for args. Okay. Let's make sure everything is running correctly. It's correct. I'm gonna check this. So 4 times 2, 8. Actually, 8. Perfect. Okay. So we have this working correctly. At least the basic one. Now let's do 2 ones. Int sum int x comma int y return x plus y, and then we do sum 3 comma 5. So this will be 8 times 2, 16. There we go. Something is wrong. Is it the number of arguments? That expression. Oh. $16. Yes. Okay, so that worked. Oh, but it's addition, so we'll never know if the argument order was correct. Let's do minus. And let's do 7 minus 5. 4. Okay, so 2 times 2 is 4. That is correct. Okay, so we have function calls working correctly. We have assignments of variables correctly. I'm just going to please commit this changes. Working variable reference, arguments, function calls, binary operators, and assignment. Alright, so now we have simple assignment statements working. Let's do conditional operators. Let's do if statement. I'm gonna go get some water. I'll be back in like 5 seconds. Okay, let's continue. Okay, now I want to do if conditions. So go to parse statement. So if conditions are easy because what we simply do is we pass the condition, we check for it being equal to 0, sorry, it being non-zero, and if it is non-zero we continue, else we insert a jump instruction, an empty jump instruction, and then later on when we finish the then, we will take the address of the else and plug it into the if. The only thing we have to be careful about is we remember the address of the start of the if, because we'll have to calculate the address where to put the else branches jump. Honestly, I guess I'll write it out as an example first. If then else requires two jumps. One is for the conditional jump that goes to either true or false, and then the true branch needs to skip over the false too. That is also important. So both need to be patched. And we will do that. Yeah, we need to remember some addresses for filling in later. I think we're close to 3 p.m. now. I could finish if conditions, get Fibonacci working, and then we can close the stream. I don't want to do loops too. Loops are kind of easy because there's no else. You just have to generate a loop back. I'm kind of getting tired. I haven't had enough sleep last night. I don't know why. Just woke up very groggy this morning. It's fine. I will do if condition. So this form of the if condition is if parentheses expression curly braces. I think we can reuse code from function body too. And then just minor statements anyway, so it's fine. It's not too bad. Okay, let's do parse statement. So if it's not token semicolon, if it's not token keyword, we should check if it's token if. Jump on equals parse if statement. This actually needs to be a call. No, sorry, this is fun. If statement can just be a jump. So we have parse if statement. Okay, let's see. What do we have here? We just consume the if. So now we consume the parentheses. Right? It has to be the parentheses, and then we pass expression. Now it's starting to get easy because we now just call functions left and right. We don't have to like do much with it. So call expression must have now pushed it on the stack. I think this is where I need to do some stack frame setup too, because we have to do some local allocations. That's okay, yeah. Parse sub if statement sub call parse if statement sub. Q. Okay. Push RPP move Q RSP to RPP, LEAQ. Let's say we need how many? 32 slacks, 4 stack slots. Okay, so let's put some comments. So -8 RBP will be used for address of conditional forward jump. Address of unconditional forward jump after then, if it exists. I mean, if the else keyword doesn't exist, we don't need it. We just need a fall through. Yeah, but we might need it. So okay, address of conditional forward jump, address of unconditional forward jump after then. So we call get token, we get the expression, this is the condition expression, right? And then we call get token, which will take the curly the parentheses out, closing parentheses, and then we do, this has to be function body. There's no changes here. Okay, so call get token, call parse expression, call get token. Now the top of the stack in the generated program is the expression value and the address of it. So before we start parsing the expression statements body, we need to first generate the condition. So we need to throw off the address first and then take the value. So we do that by 58. Should put comments everywhere. Oof. So this takes the two values off. Good. Now what do we do? Just 1 second, I need to check something. Okay, so we pop the top value. Now we need to compare if RAX is 0. So how do we do that? Yeah. So we did pop q%RAX, pop q%RAX, and then we do compare we do test qRAX. We're checking if RAX is 0, and then we do jump on 0 if condition forward jump. So this is going to require relative jumps unless I do this. So what this will do is give us like a 8-byte address where we could just put the absolute value. Avoid doing relative addressing. Okay, so this becomes our forward jump. Then we have the body of the then. So this is body of then. Then we do move q into RAX, and then we do an unconditional jump for star RAX. Then we have body of else, and this becomes the end target. This is what we'll do. Let's compile this. This is a little complicated now because we have to remember those addresses too. Paste this here. Oh, wait, a couple in the wrong place. Okay. Okay, so we wrote 5858, which was for popping the two values. Why didn't that? Because I did not compile this. I've almost written the wrong thing. Oh, conditional jump cannot take relative addressing. Oh, sorry. Number of operands mismatch for test. GSM conditional indirect jump. Is that not allowed? So do a conditional branch with an indirect jump. Alright, fine. We will not do what I was thinking. Yeah, we're only allowed to do it for this. So yeah, we could do this where we just like bake in the bytes of the forward jump. So that way we will have like fall through by negating the condition. Honestly, I think this might be easier to do than doing. You know what? I'm going to be brave. I'm going to do forward address like relative calculation. It's fine. Else part, and this is gonna be else part, and this goes away. It's gonna be if end, and there's gonna be just a bunch of knobs here for okay, so this is the pattern we have to generate. This is a short jump. Can we be sure that it will be a short jump? Like a under 256 bytes? Absolutely not. The way we are generating code, it is very, very what is the encoding of JE with a 32-bit offset? 2-byte opcode followed by 4-byte 32-bit immediate value. Unlike short jumps which use 1-byte offsets, near jumps require an escape code to access the extended jump range. Okay, so it has to be the hex encoding for JE 32 access is, yeah, first thing 30-bit in G. This is what I want. In most cases, you would use jump to target label. No, I want. How can I force a 32-bit offset in GCC? So it has a EL suffix. So this becomes JZL and it becomes JML. Nope, invalid instruction suffix for JZ. Straight up lies, huh, Gemini? Jesus, what is this? Modern G is going to specify the displacement size using a specific syntax that forces the near version. Oh wait, the N is the N one supposed to do it? Oh yeah. It's straight up lies, man. Okay, that finally worked. Makes up shit. Okay, this is fine. So we have the first 2 bytes 0f84 for jump on zero? No. Yeah, jump on 0 goes forward. So in this case it's 8 because it's jumping to here, 8a. So how much is 8a minus 8? 1. Not Python 34. So you have 0x8a minus 0x81. So that's 9. But the address where we are actually putting the constant is going to be 83, right? 0883, yeah. So 0x8a minus 0x83 is 7, but the address that we end up putting becomes 8. Sure, it's just the encoding difference. Okay, so we have to take the difference of where we are jumping minus where the constant is and add 1 to it and then store it at the constant. Okay. Let's write this code then. Okay, so we've done pop, we did the pop RX, then we do comparison. So we do move L, just to move 481 percent R14, move B $85 to $R14, move B $C0. Okay, so the comparisons have been done, and then we write the 2-byte. So move W 0x8 or 0f into 4% R14. Okay. Is it 4? 0, 1, 2, 3, 4, yeah, fifth byte. Okay. So we have that, and now we're going to just put a 0 for here. So it's going to be 0x. I mean, you don't actually have to write 0. We can just leave it blank, but for my sanity, I'm going to do this. Actually, we should finish this off first. So LEAQ 6% RIP. It is 6, right? 1, 2, 3, 4, 5, 6, 7. Oh, something is wrong. Yeah, this is wrong. Of R14 into R14. The reason I did this is I need to now store this address. So I can do move Q %R14 into -8% RBP. So this is, I'm storing the address where the jump is supposed to be, and then I can just leave 4 bytes by doing LEAQ 4 of %R14, right? So we have a 4-byte gap left, and then we can simply start parsing the body, right? JE else part. Yeah, this looks fine to me. So now, can we just jump to parse function body? Parse function body does a bunch of things. We should make a parse statement block. This is a callable parse statement block now. So we do call Q parse statement block. So this would have parsed the then condition. We should right away go and patch the jump now. So now we have the R14. We load -8 RBP into this. So move Q %R14, no, -8% RBP into RAX. And I do subtraction. So what's the sub Q instruction? Why do I keep forgetting this? It does subtracts the second operand from the first operand and stores in the rest. Okay, so second from the first. So %R14, %RAX. So this is the offset. Now we do incur %RAX. We need the address again because we have to actually make a store now. And now we do move L %RAX and %RBX. So this generates the forward patch for skipping over the then, right? And then we need to create the jump. So we do move w $0x03 e9 comma %r14 q2 of r14 comma r14. Now we again need to note this down to a stack slot. Turns out we could have just stored one stack slot because we can put them both in the same slot, because now we don't need the old one yet, but it's fine. We do move q r14 into -16% RBP. Now we can do LEAQ 4 of R14 into %R14. Great. This is great. So now we have the forward jump created, and now we do the else part. Actually, before we do the else part, we should check if this is required. If there's no else, we don't need it. Right, so this patching has been done. We do call get token compare q $token keyword else comma %rax if jump are not equal finish if statement. It just does leave and red q, right? Done with clearing up the stack. No, we need to return the token though, because the else needs to be returned. No, whatever we parsed that was not the else needs to be returned. So how do I do that? Finish if no else. Okay. Okay, so now we do the forward jump and store the address of the forward jump into this, and now we can do call q parse statement block. Parse q stall statement, this will do the else condition code, and now we need to just go back and do the same kind of patching we had done before. Move q -8 -16% RBP into RAX, move q RAX into RBX, then sub q %R14 comma %RAX, incur %RAX, move L %RAX comma %RBX. So this has patched it. The curly braces have been done, and we can simply go to finish statement. Okay. This will handle the else condition. Great. Now we just have to do parse statement block. Which I think should be very similar to the previous thing where we do call get token, compare token r brace rex jump equal parse statement block end, parse statement block end does return token and then returns. If it is not, then we do parse statement. No, sorry, this needs to. If it's not, then we return the token and call parse statement, and then we do jump statement block, right? Should be similar to parse function body. We do, oh, the curly braces need to be consumed too. Yeah, I haven't consumed that. So consume the curly braces, then do first token of the next statement. We do call the token, check for r brace. If it's equal, then we go to end. Else we call return token, parse statement, and jump to the next one. Perfect. Oh, we wrote this twice, it's fine. We can just consume this here. Well, okay. God, what did I do? Bad register name keyword if junk at the end of file. Oh, haha. Okay. 270, 271, 286. Well, this is working. Let's do. This is working still correctly. Now let's do statement. if swim statements, int x equals to 3 and y equals to 4, if x is greater than y, return 42, else return 55. Let's test if this works correctly. Parser expected type. The only place where it expects a type could be where is it expecting type? Oh. Parse if statements sub got a segmentation fault. That's fine. We can fix this. RBX. What is RBX? It seems like a valid address. No? Yeah, it seems wrong. That doesn't seem like a valid address. Just put a break. Okay. Okay, so this is what matters. It is 58A1C6. Okay. Yeah, this is wrong. How did it get corrupted? Did I mess up again? Did something use RBP? Okay, wait, I should just check the value of RBP, right? FFFDDA0. That is correct, but somehow the value is wrong. Yeah, okay, so how did this get corrupted? Part statement block. I guess we just step through it. Sometimes I use finish, it just crashes because it doesn't stop at the right place. Okay, so in the middle of parse expression now. Okay, I don't even know where we are. I'm lost. Can I go back to that parse statement? This is not helping. I'll start from the beginning. I'm gonna step through it again. Parse if statement. Yeah, it's a nice little value. I'm gonna quickly check the value of RBP minus 82. That's the one that we care about actually. Yeah? It is 8A1C6. Okay, that's what we just wrote. Okay. I think if I just call this, it's gonna fail. So I'm gonna hopefully do. God, I can't even copy these values. If I do focus CMD, then can I copy? Nope. Statement block next plus 5. Do this. Address of parse statement block next plus 5. And put a okay, 590. Continue. Finally, okay. That is RETURN. That is correct. And we want to make sure that our thing is not corrupted, but it's still correct. Okay, perfect. I'm gonna just put a watch point on that, honestly. Okay, so something noted here. How is this? What is the instruction doing it? Who the hell is calling me? Probably scam. How is this instruction causing that value to be overwritten? It has been corrupted. There's no way it happens because of move R10, AL. That is not the reason. I did reserve space for this here, right? I did a push RBP, move RSP to RBP. And then I shifted the RSP by 32. Sorry. Let's see. So the place where I use RBP for stack slots. Here. Oh, I moved RSP down. No. That would do it. That would do it. Okay, finally, it's reaching the execution but failing in this. This is fine. This we can handle. Break. Execute. Program. Run. Okay. My god, it's stuck. Okay. Loads the value of the first address. Does the comparison. Pushes it RDX. Pushes 0. Pops the value. It is 0, so it's false, right? Is it supposed to be false? X greater than Y. Okay, yeah, that is correct. Oh boy, this is bad. Okay. Okay, so this is false, is correct. So it says code gen buffer plus 57. Yeah, that's wrong. 8A B9. It should have been 8A1. Where the hell are these decal and stuff coming from? What? It should have been yeah, it's jumping to the middle of token buffer for some reason. Yeah, this is just wrong. Okay. Forward jumps are not computed correctly. Let's see what I did wrong. So move RBP RAX. This is correct. Move Q RB. Okay. Sub Q R14 RAX. I want to make sure that this is done correctly. Sub Q. Subtract the second operand. The source operand. Oh my god. Source from the first operand, the destination operand, and stores it in the destination operand. I hate this. Source from destination or destination from source. So this has to be RAX R14, but obviously we don't want R14 to be written. So we move R14 into RBX and then do this. So now the result is stored in RBX, which means we have to do enqueue also on RBX, and this becomes this. Okay, so what I'm doing now is loading the value into RAX, subtracting and moving R14 to RBX, subtracting RBX minus RAX and storing it into RBX. This isn't destination equals to destination minus source. Thank you. Then increment RBX by 1, move EBX to RX. This is good. Same thing needs to happen here. Come on, GDB. Don't do this to me. Okay, 8A1DD. That seems correct. But for some reason, the instruction is wrong. Okay, so okay, 8A1DD seems fine because that's where the jump ends. For some reason, it's just there's just corrupted instruction. There's add CL minus 31. That seems wrong. Okay. The then part seems correct. We have a move RAX, push 0, pop RAX, leave ret. That seems correct. This is also mostly correct. Like, I think I forgot to leave space for that. Zero 03 E9. Wait a second. Why is jump only 3 bytes? Huh? How do I encode an unconditional jump with a 32-bit offset? That's what I did. Also, the math for jump is different. Okay, let's look at this. What did I write here? Jump D32 if n. There's only 3 here. No, this not just showing the 0 bytes, is it? Yeah, where's the stuff in the middle? 8B. Okay, so this is 8A, 8B, 8C, 8D, 8E. Okay, so it's only 3 bytes. No, wait. The E3 is part of it. My bad. My bad. The E3 was the offset, so it was supposed to be. You know what? I'm gonna check if n is gonna get a nop 2. This is on me. This is not. Okay, so 9-2 is what I was supposed to jump from. 8B. Yeah, 9-2 from 8B. How many is that? minus 0x 8b 7, but we got 3, so this time we have to subtract 4. So instead of doing I and Q, we do Okay. So 8A. Oh. Move B. 9. This was the mistake. Okay, this went correctly. Now we do 55, which is correct. That is correct. Let's do less than. So that's correct too. Wonderful. Now let's try to write Fibonacci and see if that works. Examples, Fibonacci. Should I write factorial first? We'll do factorial. Int factorial int v, if v equals 0, return 1. Factorial of 0 is 1, right? Yes. Factorial of 1 is also 1. Oh, I can't do this without curly braces. This is the one without the if condition. So without the else, let's see if that works. Return factorial of v minus 1 times v. And then int main return factorial of 4. This should work correctly. It is not. Okay. Illegal instruction. Interesting. And the difference happens based on if I leave a space here or not, which is weird, right? Okay, it's just illegal instruction or just running bad code. Okay, what if I did else? Does that work? No, it's possible. I just didn't do the math of this correctly. That worked. And it produced right value. So okay, so the else part being missing is causing the issue. We got factorial of 4 working correctly. Let's say 6, just to make sure. 208, is that right? Factorial of 6 is 24 times 5 times 6 cannot be 208. Yeah, it's wrong. Okay. It's 5. Oh no, 256. Later on, it cannot print properly. We'll have to actually implement a printer. Okay, yeah, this is correct. Okay, so what is wrong with the missing else clause? If I do this, something goes wrong. Okay, so here, call get token keyword else. Oh, finish if else no else finish. Yeah, we need to return the token. I don't know why that matters, but it does. Nope, still wrong. So if it's compare keyword else, it's not keyword else. Don't need to finish no else. Return token. and then leave from the statement. Okay, let's check what is wrong with this. Alright, is this correct? So we do have jump on equals, jump on 0, it goes to 8AC7, which is in the middle of an instruction. That is bad. Okay. No, this is jump on, this jump on equal somewhere, which is this, and that gets a wrong offset for some reason, which is all done here before the else even arrives. It's weird. Pop push cues, if it's should end to the go to the end of the true part, right? Where are we at? We are at 8AC7. Seems like a bad instruction. Where's the... What the hell is this? I guess this is the function address. But why did it jump to 7.1? Cogent buffer plus 7.1. It should have been cogent buffer plus 66, right? What happens if I leave an empty else? Like literally do this. Then what happens? Then it runs correctly. What? it works correctly. Something is wrong with this else. I don't know what's happening. Oh, it's just the next statement isn't generated correctly. I see. So the jump it's inserting to just happens to be the fall, like the statement after the if condition. That's being generated wrong. Okay. No, but it works correctly if there's an empty else. I don't get it. What is it that goes wrong when we don't have an else? Also, I think I made a mistake. This needs to be before the patching, right? The forward jump, yeah. You don't want to jump to the jump. Right, so we do call par statement block. Then we immediately do the forward jump, which goes to the very end, and then we go and patch to the else block. This is so annoying. I'm gonna go back to what it was before. Yeah, this is just patching over like to the jump, which I actually need to debug what's happening when it's correct to. Let's do the. Something is really wrong with this. I think even this shouldn't work correctly, but somehow it's working. the weirdest kind of errors where they're not supposed to work, but they still work. Okay, so in this case, it's jumping to 7-1, which somehow happens to be after the jump. Oh, because I did the math wrong. We were supposed to jump here. So, okay. So this jump is supposed to go to else part, but the jump has to be generated first. Yep. I guess what we'll simply do is write two versions, with if and without, with else and without else. Okay, so this is the version with the else part. The jump needs to be generated before the else. Okay, so this is what generates the jump, and then we do the patching. Right? This is assuming there is a else statement. So we first generate the jump, store the address into R16, then we go back and patch the jump to end after this jump. And the target for this jump is 8F. Now make sure this is done correctly. So 0x8F minus 0x83 is 12, but we got 8, so we still have to add 4, which is I think what we did for the previous one too, for the jump too, right? We added 4. No, we subtracted 4 in that case. Right, we subtract 4. So okay, so this will patch the back, and then it goes and passes the statement block, generates patches the jump, forward jump, and then this is fine. And then if no else, we first return the token, and we still have to patch it without generating the forward jump. So then we get this here. Right, so we do -8 RPP RAX, we take the value now, do the patching, and then if statement. Okay, this should do it correctly. Okay, so this came out correctly, which was with the else. If I write it this way, it also came out correctly. Perfect. So now we have our factorial function working. Let's go. I have time and energy to do while. It's been 6.5 hours almost, but I do want to do while, so I can do factorial without recursion, and assignments would be nice. Okay, let's do while. Finally. working if then else statements and recursive factorial. Alright, let's do while statement now. So where was it? Parse statement. This will be very easy because most of the structure is already written, like parsing body is written, and like if is very similar to while in that sense, so we don't have to write too much code. This should be easy. So if it's not an if, then we do compare it with keyword. Although implementing break and continue is gonna be a little bit of work, which I think it should be easy. Shouldn't be that bad either, but we'll add that later. Okay, so then jump on equal parse while statement. Same way we'll have a parse while statement. Parse while statement, we'll have call queue, parse while statement sub, okay. So we already have the while loop. Now we do first, let's do setup. I'm gonna copy it over so I don't make mistakes. This time it's gonna be different. So -8b will store start of loop. This is like literally the start of the loop address. Like if we ever have to do like breaks or continues, we'll need this address of conditional forward jump after check. Yeah, let's throw that in R16. R8, yeah. Finish while statement will simply do leave and queue. Okay, now we have parsed the while token. We first parse lparent, so call get token, then that one is gone. Now do parse expression, call get token. This is great. Okay, now we need to write it first. We have while we do pop q %rax, pop q %rax. Oh no, actually evaluate condition, because condition needs to be evaluated every single time. We'll make it part of the start loop back. Yeah, so evaluate condition will do where no op, that's fine. Then we have pop rax for the conditions. Then we do test q $%rax, jump on 0 t32 loop done, which is loop done. Then we will have nop jump to loop back, and that's also going to be .b32, right? Okay, and then nop. So before we actually generate the condition code, we have to do store the R14 into -8% RVP. So we have that address stored. Do call get token. Good. So you do 5858. This is the 2 pops. Then we do the 3 bytes for test, which I think we can just copy over from earlier. It's the same code anyway. So pops, 3 conditions, forward jump. This whole thing is the same. Okay. It's just this one is gonna be -16 now, because this is the address of the conditional forward jump after check. Okay. So we got up to the jump, and then we do parse statement block, right? And then we immediately just do a jump back. So we do move just E9, remember, it's just E9. So move E9 to $R14. Then LEAQ oh, we already have the start of the thing, so we can just compute it and put it here. Okay. But we should do this first. So R14 is in the right position. Okay, so now we have the address of this, which is A3 in this case. I'm going to do the math separately. So 0xA3 minus 0x93. So we got 16. Now, what does the encoding say? ECFFF. FFFFEC. What is FFFFFEC in 2's complement? So it's -20. So it's the same as before, right? We take the 0x93 minus 0x83 and then subtract 4 from it. Yep. Okay. So we do move q dollar $8% RPP into $RAX. Now we need to subtract destination equals to destination minus source. Yeah, so I'll do sub q for 14 minus RAX. So RAX equals to RAX minus R14, which will set RAX to a negative number, correct? Then we do q minus 4% RAX, 1% RAX, that's good. And then we just put this value right here. Actually, this should, yeah, this is fine. We can do a move L. I can just discard the higher bits. Okay, so this generates the back loop. And then finally, we need to compute the address of that forward jump, which we just have the code for somewhere. This one. So we move R16 into RAX, R14 into RBX, RAX into RBX. Subtract, this is correct, this is correct, this is correct. Okay. So the patching is also done. And we are ready to leave. And token also hasn't been consumed. The last thing was the curly brace. I think this is it. If it compiles. 5. Is this comparing? Operand mismatch for compare. What did I write now? Which keyword while not? What is here? Oh, WHILE. It's 5 digits. Okay, this works. Let's make sure that our nothing has changed with factorial. Okay, this is good. The last thing I'm gonna do before we wrap up today is going to be implementing a simple print character function, which can print a single character, and then we'll use that to implement a print integer function using the while loop, and then we will be able to actually print the value of the factorial as opposed to, yeah, and the print character would be a library function that we will write by hand. So it will just be like a thing that gets linked into it. And I'll talk about a quick, like a very fun trick on how to link values. Okay, let's do that afterwards. Let's test while loop. So examples while loop dot c. Let's do int factorial int x. Oh, we haven't done local variables yet. It's fine. We'll do that afterwards. We'll make a global variable. Ret equals 1 while x ret equals ret into x equals to x minus 1, return ret. Yeah, we have to make forward stack slots yet. We haven't done that for local variables. That'll be easy. Return factorial of 5. That was wrong. It's not 88. Should be 120. Let's try this first. Oh, this is right. So then while x is not working, while x is just x is positive, right? I mean, x is non-zero. How am I checking the... I'm doing test RAX. And then I'm doing jump on 0. Yeah, that seems fine. I guess we can step through and see what's wrong. For some reason, this is not working. Oh, now it's working. Why was it printing 88 earlier? See? Is there some non-determinism in here? Did I make some mistakes? This is saved. Oh, it seems to be working fine. I think I must have not saved the loop from file or something. Okay. So this is good. We have while loop working. Quickly try some corner cases too. With 1. Okay. Save. This is correct. What about 0? One. Perfect. Okay, so factorial is working correctly. Yeah, we just do a print function. Okay, so for printing functions, we need to implement a library, basically a library routine that can print a character that we supply. But the problem is there are things that this function needs that we cannot write it in C itself, right? Like it needs to make a system call, which we don't have a syntax for. Now we could actually just provide a system call function. The problem is the ABI is not going to match because syscall is, I mean, we'll have to provide a syscall routine at least. Maybe that's the best way to do it. Maybe we should just provide a syscall function that can then be used to write whatever syscalls we want. Yeah, but we don't have address of and stuff like that implemented yet, which is what you would need. Like, you have to make a local variable where you will put the value and take its address and send it into syscall. For now, let's just do a print character function, a basic print character function. So the way we do this is we go to our identifier table, which is defined in tokenizer, and just like we had added main, now we'll also add put char, right? Put char. How do we? If I just put one here, that will give me the value, right? Yeah, so this is our encoding. But the problem is the way this gets passed is higher bytes going to, how many characters are these? 1, 2, 3, 4, 5, 6, 7, 8. Wait, it's exactly 8? Oh, perfect. Then we don't have to worry about it. So this will fit into one register. Yeah, just copy this. Okay, so this goes into our symbol table. No, this is not a symbol table. This is the this is our identifier table. And now what we do is this is clearly identifier number 2. This is identifier. This is identifier 0. This is identifier 1. Right. We go to the global table. Global symbol table, and we just preload some entries into it. So instead of, first of all, this needs to be moved into the data section now, because, which is annoying. We do that, and then right. So this actually needs a little bit of trick. So we do global symbol table, and then we put our dummy entries here, and then we have global symbol table start. This way we don't overwrite the values, and then we do space 40960, right? Yeah. And then we can remove this and put this here, and the global symbol table, this becomes global symbol start. So that way we don't override the existing values. That's the only thing. Yeah. And now we put the actual values. So we have 4 bytes, 24 bytes per identifier. The first is gonna be the identifier index. So we know that tokenizer 1 put char is 1, so that goes into 1. Then we need the code gen address. Now the cool thing is we can just put the address of the function here. So we can say libc put char, right? Let's call it x86c libc put char. This is like our user defined function that can like be just linked into it, and then it needs a type of variable which we can just leave as 0. It doesn't matter. The type is it's supposed to be the return type of it, the return type of the function itself. So what does put char do? Void. So what is void keyword? I think it's just keyword underscore void, right? Yeah, void. So now we have a entry in the global symbol table that's pre-filled, and the address is already pointing to x86 libc putchar. So we just have to implement this, and that's it. src x86c libc.s. Okay. This is very easy to implement. We just have to follow the same ABI as what the previous function was following. I mean, all our functions are following. So this gets fine. We do global. What did we call it? Okay. So what did we do? Push q rbp, move q rp, %rbp. We don't need any local variables for this one, so this is fine. We just need to get the first address, which we devised to be at -6 at rbp plus 16. So then we do, okay, we have to just get the API for the write system call, and we just need a dot data. I can put it on the stack, it's fine. Let's put it on the stack, make it self-contained. So then we need to do leaq -8% rsp, %rsp. Okay, so we have made a stack slot, and then we move stuff into it. So actually, we already have the byte on the stack. We actually don't need to copy it anywhere, right? The argument is already on the stack. We just give its address. So leaq -16% rbp, no, plus 16 rbp, 16 rbp into RSI. See, write system call Linux system call list. Right, so we have the first is the write system call, that's fine. RSI gets 64-bit. This is the same thing, right? Scroll table 64-bit, come on. Hold on. We need write. Can you just tell me where the registers need to go into? Here. Okay, so sys write fd buffer count. Okay, so fd for std out is what, 0? Std in is 0, std out is 1. I mean, I have already written that, so I should just copy over. Move q $1 into RDI, right? Yeah, RDI gets the file descriptor number, RSI gets the buffer, and we give it the size. Move q $1 into RDX. Right? RDX, right? Yeah, okay. And then we do syscall. No, before that we do move q. Syscall number is 1, so $1 into %IX. Syscall number is also set, and then leave red. Okay, so what we've simply done is simply wrote a single like libc function that gets linked into whatever our programs will be. Now the part is when we actually get to the point where we start writing these into an actual file, that's when this will get tricky, because that's when we will have to like also write this to the final executable. The way we'll do that is we will just have this in a separate section and we'll just copy this over into the code gen area, or we will pre-fill this into the code gen area. So that way, when we write everything to the file, yeah, instead of putting it in the, like, the text section directly, we'll put it into like the code gen area to begin with. So that way, it'll always be part of the executable. Okay, so this is fine. We just need to try this out. So examples put char.c. In this one, I'm just gonna do a hello world. If I can figure out what the ASCII codes for hello world are. Okay, I'm just gonna write this for x in hello world print put char /t put char space plus ord of x plus space semicolon /n. Unexpected indent. Okay. This is what we needed. This is simple hello world. And we need to have a return 0. Otherwise, I don't know how this would crash. Yeah, I guess RX just would be random values. So that's okay. But this should work. Okay, there's some issues. We'll fix those and we'll be good. Undefined reference to global symbol table. That's weird. Oh yeah, I never named it. Okay, no such instruction global symbol table. What? I'm defining a label. No such instruction global symbol table. Oh, that was weird. Okay. Oh yeah, I forgot to save it. Okay. Invalid identifier. Okay, so something went wrong. I'm guessing putchar didn't get decoded correctly. It just got invalid identifier. Must have not found it in the global symbol table. That's okay. We can debug this. parse identifier expression. So the token has already been passed. Let's check what it is. It is token and RBX is 2. So never run another man's rhubarb. Huh? Okay, so I think the indices are just wrong. For some reason main is 1. Yeah, okay. Let's look at execute, right? Execution area. No, identifier of main is 0. I guess I'm getting a bunch of spam, but that's okay. And if index of main is 0, why is this not correct then? Tokenizer. If it doesn't match exactly, it's possible that it added a separate entry for putchar. Did I not encode it correctly? Oh wait, did I put 0x? Yeah, I did put 0x, okay. Because I've done that in the past. Cat encode keywords. Of course it doesn't print. Okay, this is what it produced. Wait, is underscore not being parsed correctly? Seems correct. No, this is wrong. Wait, what? Where did 4.5 come from? I just encoded wrong earlier? What had I done? Hey, where's this 4.5 coming from? Put underscore char. What did I encode just now? Wait, this is weird. 4.5. Oh no, it is correct. It is correct. I was just looking at it. Okay. I think what's happening is the parser might be stopping at put underscore. I think tokenizer we might have messed up. Let's see, where is underscore? ASCII table, ASCII table. Stop clicking on random tables. Underscore is 95, which is, yeah, I think it gets passed. So I think we were checking it as between between 65 to 122 as all being identifiers, right? 64 to 123, yeah. I should just check how the thing gets tokenized. I just put char not getting the right token. That's the last thing. is it? Keyword and this one. Okay, the first one is gonna be main, so we can skip this. The second one is what we want. Okay. Okay, this point. What the hell? What does it read into? RBX, sorry. $66,169.60. That sounds like main. No. Sounds like char. M A, yeah. Oh, the first one was int. Okay, so we'll continue from here. This one is what we want. This will be put char, right? Yep. 2, 3, 4, 5, 6, 7, and it goes shift and continue. Okay. Oh, it overflowed. Okay, and then the last one. Okay, okay, this is perfect. Oh, it got moved to RCX. Why did it get moved to RCX? We should shift only if then return works correctly. RETURN. No, return was small. RETURN. Okay. Okay, so the problem is for exactly 8-letter words, it's shifting preemptively. We need to shift back it down. Okay, this was an issue. So shift and continue. Read till end. Checks if the highest bit is high. If it is high, then it shifts. Right, so what needs to happen is this shifting only needs to happen if we are appending to the register. So don't preemptively move before. So we load the value first, right? We load the value, increment R10, and then we test AL. Okay, we just test AL first. If it is 0, then go to get token end, which is like end of file. If it is 33, less than 33, which means it's space, and we consume spaces. And if it is actually more than this is now it's ready to be written. So now before you write, make sure that it's not overflowing. So this goes to, no, we can't put to RCX, we need some other register. RBX, RDX, RCX, RSI are all three. I'm going to use RDI. Wait, why can't I use No, because we still have just because if it's jump on node 0 shift and continue shifts everything, and then we do this, which shifts it again by 8 and then adds RPX. Okay, and if it wasn't, it would add, it would normally shift, right? Okay. And then you add the value into the register and then till the end. Okay, this solves it. Yeah, we got hello world. So this is what we are expecting. I just want to quickly make sure that factorial is also working correctly. Is while's loop working correctly? What is while loop supposed to be? Well, just factorial of 0. Okay. That seems to be working correctly. Hello world. So now what we will simply do is, in our factorial itself, write a function that prints numbers, right? So examples factorial. This is a recursive version. That's fine. We'll say void write integer or put integer. Now the cool thing is we can just implement this using our language, so we don't have to do complex like linker tricks. So we just get an integer, and this time we can use a while loop. So we can simply say while x, right? While x is so what's the math for this? We start from the, you have to print the first highest letter. I need to do a I2A implementation. Can you write a simple I2A function with a while loop? Not in assembly. Oh god. Let's see. This requires reversing. Is there a way to write a version without reversing? Without having to reverse at the end and just directly call putchar. Recursion, let's go. So the way that works is putchar is fine. Oh, we write along the way back. Okay, so we do if nx is less than 0, we do putchar of, we haven't done character constants yet, so we'll do that later. 45, okay. And we have n equals to n minus 1, so x equals to 0 minus x, made it into a positive number. Okay, now the recursive case, if x divided by 10 is not equals to 0, we can just put it like this. We can say I to put integer x divided by 10. I'm just like getting used to writing writing like with spaces everywhere. This is amazing. And then finally I say put char of x modulo 10 plus ord of 0, which is 48. Yeah, so this will print the number correctly. And now instead of returning the factorial, we can simply do put integer of factorial 5. Let's see if this runs. Floating point exception, code dumped. Okay, something goes wrong. Let's leave stuff out first. So let's delete this and see what happens. Okay, so I did print plus. Okay, I guess division itself is causing issues. We never tested division, did we? We did test division. Why is it getting floating point exception? How do you use floating point exception? I guess the uninitialized RDX is coming to bite us in the division instruction. Why is that giving floating point instruction? Oh wait, this also shouldn't be like this. This should be like this. Oh, we don't support expressions like this yet. So okay, we need to do something. We do x equals to x divided by 10 and then x plus 48. Okay. I'm getting floating point exception. Let's check. Yeah, it's IDiv. Should check the values of the registers. Register values unavailable. Interesting. Let's check. Okay, so let's check what IDiv instruction is. So IDiv has, when you do IDiv with a single instruction, it does sign divide RDX RAX by R64. Results store into, so RDX need to be cleared out. Okay, I'm gonna quickly try something and that might just do it. So we go to binary operator. There's somewhere where we do RCX being cleared, right? I'm gonna clear RDX too. Here, and I think this one is RCX clear. We just need RDX clear instruction. Technically, we have to use the sign extension version of RAX. So that way, if it's a negative number, it stays a negative number, but I think this should be fine for now because we already made the number positive. 4831 D2. D2 31 48 percent of 14. Okay, it printed something, not 120, but something. to 0 plus 48, it does print 0, 0, 0. So that's good. Why doesn't it work with x? 0, 1 weird character. Oh, this should be modulo, not 10. That is wrong. N modulo 10 plus 0. And on the unwinding part, I can modify x, right? Like, it's not a problem. No, because we didn't copy the arguments back. Like, no, this should have been fine. Yes, when it takes the address, it takes the address of the arguments, but that's okay because it already has a separate stack slot. What is wrong? Why is this doing x equals to x modulo 10? What are these numbers? We should just put a breakpoint and put chars and see what we get. No, it's break x86c libc put char. Okay, the first time we got RSP plus 8 plus 16, 31. I'm confused. Oh, it stops after the initial setup. That's weird. Anyway, so okay, so 0x31, which is 1, right? Are you kidding me? Actually, I can just do, yeah. It's 31. 14. 4 ka, right? Okay, I'm gonna do some easier debugging. I'm gonna say put void put integer put int x. I'm gonna manually just unroll this like 4 times and say int a, int b, int c. So the negative is not required, so we simply say a equals to x modulo 10, x equals to x divided by 10, b equals to x modulo 10, equals to x divided by 10. C equals to x modulo 10. X equals to x divided by 10. And then we do put char C, put char B, and put char A. And we're going to test put int, not put integer. Printed x for some reason. Let's not do this factorial stuff. Let's just do 1, 2, 3. Okay, this itself is wrong. I did 46, 46, 47, and 48. That is wrong. Oh, so it should be 49, 50, 51. This is correct. So now let's do C plus 48, B plus 48, A plus 48. And that's garbage. Okay, so the modulo and something is causing things to be wrong. Is it the modulo? Is it the division? Okay, I'll just do the debugging then, I guess. Wait, I never call factorial, right? Just to make sure. Yeah, just put 1, 2, 3. Okay. I think it's modulo that's causing issues. Okay, let's do this. It took a lot of functions to get there. There are global variables too. Okay. Okay. Jump to this function, which is the put integer function. Okay. And this is where the actual subtraction happens. idiv rbx. So at this point we should check what? It's pushing rax. It's 3c. So just c. And what is rdx? Is 3. Yeah, I think we just encoded it wrong. For modulo. Wait, what the hell is modulo? Never added modulo. How did it work then? Why did it not complain? this was bizarre. Okay. Token percent. Token percent is almost the same, except instead of division RDX, we return, sorry, RAX, we return RDX. Right? Here. So IDQ push RDX, that's what we need. This one. I think it says 52 instead of 50. Okay, I think this should be correct now. Hey, we got 123, okay. Which is at least the correct characters. Okay, this is fine. Let's remove this and call put integer. And we got 123, which is correct. And if we do factorial of 5, we get 120. Yes, that's working. Finally. Wow, hold the phone, just realizing you're writing a C compiler in ASM. Yep, that is what I'm doing exactly. And we just got to the point where we can compile recursive functions, if conditions, while loops. We can compile printing of characters, and we wrote a simple integer printing routine that can print the factorial of a number. Yeah, I think this is where we'll stop though. We have been going for 7.5 hours. I think I need to rest. I got to the point where I can compile for factorial, which is great. Yeah, I can get 120 out of it. I should just put I want to write a /n, so I can just do that here, right? Yeah, that's fine. What is /n? 32, right? Nope, 32 is space. What is /n? Interesting. I just popped in 10 minutes ago and I was wondering, and copped C being the source lang. Learning C of nodes currently as a hobby. Are you streaming on YouTube as well as, or just Twitch? No, so I'm doing mostly on Twitch, and then I post it on YouTube. If you want to watch what's been happening so far, there's this, under my picture you should see a website which has everything about this project. So it has the GitHub link, it has the Twitch stream link, and it has the YouTube where I post all the videos. And this is part 2 of the stream we did last weekend. We did another 7.5 hours of stream where we wrote the tokenizer, basic parsing of integers and so on. And now we have got to more operators, and we have statements and stuff. Yeah, I'll post today's version on YouTube within like a few hours, whatever amount of time it takes to upload. But the Twitch should also have this for a while, so you can all just go back and watch on Twitch. I think both the videos are on Twitch right now, so you can watch those if you're interested. Awesome. Yeah, I'll sub on YouTube anyway, so catch you again. Perfect. Thank you so much. I appreciate it. Yeah, I posted the last week one on YouTube already. It's a little long, and I tried to make today's more interactive. The last one was more me just writing code. I couldn't interact as much as I wanted to, but this one is, yeah, definitely. I was explaining every single thing I was doing. Yeah, what was the last ASCII table for a new line? Carriage return 13, so this should be 13. And that printed nothing. Oh, not carriage return. We have to, what's new line? Line field. Okay, so now we get this working correctly. Okay, just gonna commit everything. Examples, factorial, source parser, source tokenizer, examples, putchar, examples, while loop, source x86 libc. Oh, I did not. What? Did something wrong. And now my keyboard is broken. That's what happened. Not keyboard, the. Let it. Okay. Working factorial iterative and recursive and working printing numbers. Then that's it for today, folks. I think I'll wrap up here. Oh, we should test the while loop version here too. Yeah, the next thing I'll do is local variables. I have been avoiding doing local variables. I'll do that next. That works. It's okay. Just making sure everything is working. Okay, cool. All right, folks, that's all for now. I'm gonna wrap up and go back home and get some sleep. Thanks for attending. I hope you had fun.